Hello there, and welcome to the Cosmographer. Somewhere on this list is the reason there is something rather than nothing at all, and no one can fully explain it. So is the invisible material that outweighs every star in every galaxy by 5 to 1, still unidentified after 50 years. So is a force that makes empty space push itself apart, and that disagrees with our best calculation by more orders of magnitude than any prediction in the history of science. There is a particle that arrived carrying the energy of a thrown ball in a single speck of matter from a direction that looks empty. There is a silence where a galaxy full of voices should be. Over the next 3 hours we will walk through 14 of these, calmly, one at a time, all the way to the final question of how the universe ends. Make yourself comfortable and settle in. Hit subscribe if you're new here, because by the end of this list, the sky will look a little different and a little larger. Now, let's slowly work our way through it, beginning with the missing mass. Part 1. The missing mass. We know a great deal about the universe. We can trace it back almost 14 billion years, to a moment when everything we can see was smaller, hotter, and closer together. We can weigh distant galaxies, measure the temperature of empty space, and read the light of stars that died before the sun was born. And yet, for all of that, there is a plain and slightly uncomfortable fact at the center of modern astronomy. About 95% of the universe is made of things we have never directly seen. Only about 5% is the ordinary matter we understand, the matter that makes up stars and planets and the atoms in your hands. The rest is 2 kinds of darkness we can measure but cannot name. This is a list of the things we still cannot explain. Not fringe ideas, not conspiracies, not stories invented to unsettle you. These are the honest, open questions that working astronomers and physicists agree are unsolved, laid out one by one, with the names and dates and numbers kept in. Some of them concern the largest structures in the cosmos. Some concern a single particle. Some concern why there is anything here at all. We will move slowly, and we will not pretend to answers we do not have. There is a particular calm in being told the truth plainly, including the truth about where the truth runs out. And the honest answer, again and again on this list, will be the same. We do not know. And that is not a failure. It is simply the edge of the map, drawn as carefully as we can draw it. We begin with the most abundant kind of matter in the universe, which happens to be the kind no telescope has ever seen. It has a name that is really a confession. We call it dark matter, and the word dark does not mean black or hidden in shadow. It means that this material does not interact with light at all. It gives off no glow. It casts no shadow. It does not reflect, absorb, or bend the light that falls on it in any way we can catch directly. If you filled a room with it, the room would look empty. And yet this invisible material outweighs every star, every planet, and every glowing cloud of gas in the universe by roughly 5 to 1. Ordinary matter, the matter of the periodic table, is the minority. The universe is mostly made of something else. The first person to notice began his work more than 90 years ago. In 1933, a Swiss astronomer named Fritz Zwicky was studying a group of galaxies called the Coma cluster, a swarm of galaxies bound together by their mutual gravity. He measured how fast the galaxies were moving, and he found something that did not add up. They were moving far too quickly. The visible matter in the cluster, all the stars in all those galaxies, did not have nearly enough gravity to hold the swarm together. At those speeds, the cluster should have flown apart long ago, scattering its galaxies across the sky. Something unseen was holding it in place. Zwicky called that something Dunkel Materie, the German phrase for dark matter, and for decades almost no one took the idea seriously. The evidence that changed astronomy came later, and it came from a quieter, more patient kind of measurement. In the 1970s, an American astronomer named Vera Rubin, working with an instrument maker named Kent Ford, set out to measure how fast stars orbit inside spiral galaxies. This sounds like a small question. It turned out to be one of the most important measurements of the century. Here is what they expected. In our own solar system, The planets closest to the Sun move quickly, and the planets farther out move slowly. Mercury races around in a matter of months. Neptune takes almost 165 years to complete a single orbit. That pattern comes straight from gravity. Most of the mass, the Sun, sits at the center, so the pull weakens the farther out you go, and the outer planets can afford to move slowly. A spinning galaxy, they thought, should behave the same way. Most of its glowing matter is concentrated toward the middle, so the stars at the faint outer edge should orbit slowly, trailing behind like the outer planets. That is not what Rubin and Ford found. Picture the scene for a moment. It is the early 1970s, in a domed observatory on a mountain, in the small, cold hours when the sky is steadiest. Vera Rubin sits at the instrument, feeding starlight through a spectrograph, reading the motion of stars from the way their light shifts. She works outward from the bright center of a spiral galaxy toward its dim edge, measuring the speed of the stars at each step. The inner stars move fast, as expected. She keeps going. The next stars out are just as fast, and the next, and the ones beyond that. The line that should bend downward, that should show the outer stars slowing, simply refuses to bend. It runs flat, star after star, all the way out to the visible edge and past it. The outer stars are moving as quickly as the inner ones, as if the galaxy were far heavier than its light suggests, as if every spiral were wrapped in an enormous unseen weight. She checks another galaxy, and another, and the pattern holds. The invisible has announced itself, not with a flash, but with arithmetic that will not come out right. That flat line is the fingerprint of dark matter. To keep those outer stars moving so fast, each galaxy needs far more mass than we can see, and that extra mass has to reach out well beyond the glowing disk, forming a great invisible sphere, a halo, in which the bright galaxy sits like a coin in the middle of a beach ball. When astronomers add up how much is needed, the answer is stark. In a typical galaxy, something like 85% of the matter is invisible. The stars we admire, the part we can photograph, are a thin, bright minority riding inside something far larger. There is something worth pausing on in how this discovery was made. Vera Rubin did not find dark matter in a single dramatic night. She found it by measuring galaxy after galaxy, carefully, for years, building a case so consistent that it eventually became impossible to argue with. For a long stretch, the wider field was slow to embrace what her numbers were saying. She kept measuring anyway. The invisible majority of the universe was revealed not by a lucky accident, but by patience, by someone willing to do the same exacting measurement over and over until the sky admitted what it was hiding. It is a very human way for a discovery to arrive, and worth remembering as the numbers on this list grow stranger. Since then, the evidence has arrived from several completely independent directions, which is what makes dark matter so hard to dismiss. When light from a distant galaxy passes near a large mass on its way to us, the mass bends the light, the way a lens bends a beam. Astronomers can watch that bending and weigh the object doing it. Again and again, the amount of bending calls for far more mass than the visible matter can supply. There is more there than we can see. The clearest single example is a place called the Bullet Cluster, where two enormous clusters of galaxies have collided and passed through each other. The hot gas in the two clusters, which is most of their ordinary visible matter, slammed together and slowed down in the middle, glowing in X-rays. But when astronomers mapped where the gravity actually was, using the bending of light, they found the mass had sailed on ahead, sitting apart from the glowing gas in two clumps out to the sides. The gravity and the visible matter had come apart. That is very hard to explain if all matter is the matter we can see. It is exactly what you would expect if most of each cluster's mass is dark matter that barely interacts and simply drifted through the collision untouched. And there is the oldest light in the universe, the faint glow left over from the young cosmos, which we will return to later on this list. The pattern in that ancient light only fits the measurements if dark matter is real and makes up about a quarter of everything that exists. Roughly 27% of the universe is this invisible material. Compare that to the 5% that is ordinary matter, and the imbalance is plain. For every gram of the stuff we understand, there are more than 5 grams of something we do not. So what is it? This is where the honesty of the list begins. We do not know. We can say what it is not. It is not ordinary matter that is simply too dim to see, because we have counted the dim things, and there are not nearly enough of them. It is not made of the familiar particles in the same proportions, because those would have left fingerprints in the early universe that we do not find. The leading idea for many years was that dark matter is a new kind of particle, something that feels gravity but ignores light, drifting through everything, through the walls, through the earth, through you, billions of them passing every second without a touch. Physicists gave the favorites names, weakly interacting massive particles, shortened to WIMPs. Axions, a different and much lighter candidate. For decades, patient experiments have waited in silence for one of these particles to bump into a detector, tanks of liquid buried far underground, shielded from every other disturbance, watching for a single faint knock. So far, the knock has not come. Detector after detector has grown more sensitive, ruling out more possibilities, and still nothing has been caught in the act. That silence is itself a kind of clue, though no one fully agrees what it is telling us. Perhaps the particle is stranger or lighter than we guessed. Perhaps we are looking in the wrong place. And there is a bolder possibility that a minority of physicists take seriously. Perhaps there is no dark particle at all, and instead our theory of gravity itself is slightly wrong at the scale of whole galaxies, so that the same starlight we have been trying to explain with invisible mass is really telling us that gravity behaves differently than we think. That idea has its own difficulties, and it struggles to explain places like the bullet cluster, but it has not been fully ruled out either. Whichever way it turns out, the situation is remarkable to sit with. For more than 50 years, we have known that the most common form of matter in the universe is present in every galaxy, shaping the sky we see, holding the great swarms of galaxies together, and steering the growth of everything. It has been in front of us the entire time, measurable, mappable, undeniable, and we still cannot say what it is made of. The most abundant material in the cosmos remains, in the most literal sense, unidentified. It helps to picture the shape of a dark matter halo, because it is unlike the galaxy we actually see. The bright spiral, the part that shows up in photographs, is a flat disk, a thin plate of stars turning slowly around its center. But the dark matter is not flat. It forms a rough sphere, a great rounded cloud that extends far beyond the visible edge of the galaxy, several times wider than the starlight, enclosing the disk the way the clear flesh of a fruit surrounds its small bright pit. The stars we admire are only the part that lit up. The larger galaxy, the true galaxy by mass, is the invisible sphere in which the visible one is embedded. When you look at a photograph of a spiral galaxy, you are seeing the small, bright exception and missing the large, dark rule. This changes how we understand galaxies themselves. A galaxy is not really a collection of stars that happens to hold together. It is a well of dark matter that has gathered ordinary matter into its center, where that ordinary matter cooled, sank inward, and lit up as stars. The dark matter came first, sculpting the gravitational hollow, and the visible galaxy formed inside it afterward. On the largest scales, this same invisible material forms an enormous branching network across the whole universe. Long filaments and threads of dark matter, with galaxies strung along them like water beads on a spider's web, and great empty spaces in between where almost nothing lives. That network is often called the cosmic web, and it is the scaffolding on which every visible structure hangs. Without the dark matter to build it, the ordinary matter of the universe would never have gathered into galaxies at all in the time available. The bright cosmos is the frost on a window. The dark matter is the shape of the glass beneath it. The measurements have only grown firmer with time, and from more directions. Beyond the rotation of single galaxies and the swarming of galaxy clusters, there is the way whole clusters bend the light of everything behind them, acting as enormous natural lenses. The amount of bending reveals the total mass, and again that total towers over the visible matter. There is the temperature of the hot gas that fills galaxy clusters, glowing in X-rays, which is so energetic that only an enormous unseen mass could hold it from boiling away into space. And there is the detailed pattern in the oldest light of the universe, which fits the data only when a specific quantity of dark matter is included, a quantity that agrees, remarkably, with the amount the galaxies and clusters demand. Several completely different measurements, using completely different physics, all point to the same invisible ingredient in the same amount. That agreement is why almost no astronomer doubts that the effect is real, whatever its cause. The hunt for the particle itself has been one of the most patient efforts in the history of science. Far beneath mountains and in old mines, far below the surface where the constant rain of ordinary particles from space is filtered out by the rock above, physicists have built exquisitely sensitive detectors, tanks of cold liquid watched by banks of light sensors, waiting in the dark for the faint flash that a passing dark matter particle would produce if it ever nudged an ordinary atom. Each generation of detector has been larger and quieter than the last, ruling out more of the places the particle could be hiding. And through all of it, the flash has not come. This does not prove the particle does not exist. It only means that if it exists, it is more elusive than the simplest guesses supposed. The silence has pushed physicists to consider stranger and lighter candidates, and to build new kinds of experiments to chase them. There is a useful way to feel how strange this situation is. Imagine you could switch off, one at a time, every source of light in the universe, until only gravity remained visible to you, drawn as a glowing map of where the mass truly is. The bright galaxies you know would shrink to faint specks buried inside enormous glowing halos, and between the galaxies, long luminous threads would stretch across the darkness, a whole architecture of mass that gives off no light of its own. That glowing map would be the real universe by weight, and the starry sky we actually see would be revealed as a sparse decoration scattered across it. We have spent all of human history studying the decoration, and only in the last century have we begun to measure the structure beneath. The most honest thing we can say about that structure is that it is there, that it is most of everything, and that we do not know what it is. That is the first mystery, and it is only half of the missing universe. The invisible matter we have just described at least does what matter is supposed to do. It pulls things together. But the larger part of what we cannot see does the opposite. It pushes the universe apart, and it grows stronger the more we study it. Part 2. The force that pulls everything apart. If dark matter is the mystery of the missing mass, then dark energy is the mystery of the missing majority. It is the single largest component of the universe, larger than everything else combined. Roughly 68% of the entire cosmos, more than 2/3 of all there is, appears to be made of it. And where dark matter pulls things together, dark energy does the opposite. It pushes space itself to expand, and it makes that expansion speed up over time. Put dark matter and dark energy together, and you have the 95% of the universe we have never seen. Everything on this list, every galaxy and star and mystery still to come, is happening inside a cosmos that is mostly two forms of darkness we can only describe by what they do. To understand how we found dark energy, we have to go back to the late 1990s, and to a measurement that was supposed to answer a much simpler question. Astronomers wanted to know how fast the expansion of the universe was slowing down. That the universe expands had been known since the 1920s, when Edwin Hubble showed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. Space itself was stretching, carrying the galaxies along with it. For most of the 20th century, the natural assumption was that this expansion had to be slowing. Gravity pulls, after all. All the matter in the universe should be tugging on all the other matter, gently applying the brakes to the expansion. The only real question was how hard the brakes were being applied. Slow it down enough, and the universe might one day stop expanding and fall back together. Slow it down a little less, and it might coast outward forever, gradually easing off. Either way, the expectation was clear. The expansion should be decelerating. two teams of astronomers set out, independently and in competition, to measure exactly how much. One was called the Supernova Cosmology Project. The other was called the High Z Supernova Search Team. Both had the same clever idea. They would use a particular kind of exploding star, a Type 1a supernova, as a measuring stick. These supernovae are precious to astronomers because they all detonate at very nearly the same true brightness. If you know how bright a thing truly is, and you measure how bright it appears from Earth, you can work out how far away it is, the same way you could judge the distance of a candle of known strength across a dark field. And because their light also tells you how much the universe has stretched since the light left, each supernova becomes a marker of both distance and time. Measure enough of them, spread across billions of years, and you can chart how the expansion has changed over the history of the universe. In 1998, both teams reached the same answer, and it was the opposite of what everyone expected. The distant supernovae were fainter than they should have been. Fainter means farther. The far-off explosions were sitting at greater distances than a slowing universe could account for. The expansion was not decelerating at all. It was accelerating. Something was pushing space apart faster and faster, overpowering the gravity of all the matter in the universe, and winning. The result was so surprising that both teams checked it exhaustively before they believed it, and it was surprising enough that the leaders of the two teams shared the Nobel Prize in Physics in 2011. The universe was not coasting to a stop. It was accelerating outward, and no one had ordered that. The name we gave to whatever is responsible is dark energy, and once again the name is mostly an admission of ignorance. It is not energy in any ordinary sense you could store or use. It is a placeholder for a repulsive influence that fills all of space and drives it to expand. And here the mystery deepens rather than resolves, because when physicists try to say what dark energy actually is, they run straight into one of the strangest numbers in all of science. The simplest description of dark energy is an idea that goes all the way back to Albert Einstein. When Einstein first wrote down his theory of gravity, he added a term to his equations called the cosmological constant, a kind of energy built into empty space itself. At the time, he added it for the wrong reason, to try to hold the universe still, and when the expansion was discovered, he removed it, and, by one account, called it his greatest mistake. The irony is that his discarded term has come back as the leading description of dark energy. An energy woven into the vacuum, into empty space, would push exactly the way dark energy pushes, and it would grow in total influence as the universe grew and made more empty space. The picture fits. The trouble is what happens when we try to calculate how much energy empty space should contain. Modern physics does not treat the vacuum as truly empty. On the smallest scales, it is a restless thing, filled with particles flickering in and out of existence, a kind of constant quiet activity in what looks like nothing at all. That activity should carry energy, and in principle we can add it up. When physicists do the calculation, the answer they get is larger than the amount we actually observe by an almost unspeakable factor. Depending on how you count, the prediction overshoots reality by up to 120 orders of magnitude. That is a 1, followed by 120 zeros, a number so far beyond everyday experience that comparisons fail. If the theoretical value were correct, space would have torn itself apart before a single galaxy could form. It did not. The real value is fantastically smaller and almost exactly the right size to allow a universe like ours. This mismatch is sometimes called the worst prediction in the history of physics, and it is not hyperbole. It is simply the gap between what our best theory of the vacuum says and what the sky shows. To sit with the scale of it for a moment, the actual energy of empty space, spread across the cosmos, is astonishingly small, on the order of a few atoms worth of energy in each cubic meter of space. And yet, because space is so enormous and matter is so thinly spread, that faint energy adds up to the dominant component of the universe. The most powerful influence on the fate of everything is also one of the most dilute things imaginable, a whisper of energy per cubic meter that multiplied across all of space outweighs every galaxy that has ever formed. There is one more turn to the story, and it is recent enough that it is still unfolding. For a long time, the working assumption was that dark energy is truly constant, unchanging through all of cosmic history, exactly the cosmological constant Einstein wrote down. But very large surveys of the sky, mapping the positions of millions of galaxies to trace how the expansion has behaved over billions of years, have begun to hint at something unexpected. The strength of dark energy might not be perfectly constant after all. It might have been slightly stronger in the distant past, and be easing a little now. The hints are not yet certain, and careful astronomers are treating them with caution, because a claim this large demands the firmest possible evidence. But if it holds, it would be a genuine surprise, because a dark energy that changes over time behaves differently from a constant, and it would reshape our best guesses about how the universe ends. We will come back to that at the very end of this list, because the fate of everything hangs on this one question. For now, notice where the honest accounting leaves us. We know dark energy exists because we can watch it accelerate the expansion of the universe across billions of years. We know roughly how much of it there is, more than 2/3 of everything. We know it fills all of space and pushes outward, and we cannot say what it is. We cannot even get our theory of the vacuum to agree with the measurement to within 100 orders of magnitude. The largest single ingredient in the universe is, at present, a number we can measure precisely and explain not at all. There is a strange symmetry between the first two mysteries on this list. Dark matter and dark energy together are the invisible 95%, and they work against each other, one pulling structure together and the other driving it apart. The whole history of the universe and its future is a contest between these two things we cannot see. Everything else on this list happens on the thin, bright surface of that contest, in the 5% we can actually touch. It is worth lingering on why the exploding stars make such trustworthy measuring sticks, because the whole discovery rests on them. A Type 1a supernova happens when a dense stellar cinder called a white dwarf, the burned-out core of a sun-like star, pulls in matter from a companion until it crosses a precise threshold of mass and detonates. Because that threshold is nearly the same everywhere in the universe, the explosions are nearly identical in their true brightness. That is the gift. If every lighthouse in the world shone with exactly the same lamp, you could judge the distance to any of them just by how bright it looked from where you stood. The supernovae are those matched lamps scattered across billions of years of cosmic history, and by comparing how bright they truly are to how bright they appear, astronomers can measure distances across almost the entire observable universe. The moment of discovery was a slow dawning rather than a single flash. Both teams, working in competition, kept finding that their most distant supernovae were slightly too faint, which meant slightly too far away. At first, this looked like an error, because it pointed toward a conclusion no one wanted to announce. Each group checked for dust that might be dimming the light, for changes in the explosions over cosmic time, for every mundane explanation they could think of. The dimming survived every test. By the time the two rival teams arrived independently at the same impossible answer, the result had the weight of something that had tried hard to be wrong and could not manage it. The universe was speeding up, and two groups who would have loved to catch each other in a mistake had instead confirmed each other. There is a subtler puzzle hidden inside dark energy that deepens the mystery, and it is sometimes called the coincidence problem. Dark energy and ordinary matter behave very differently as the universe expands. Matter thins out as space grows, its influence steadily weakening. Dark energy, if it is truly built into the vacuum, does not thin out at all. Every cubic meter of space keeps the same small store of it, so as the universe makes more space, dark energy's total sway grows. For most of cosmic history, matter dominated, and the expansion was slowing. Only relatively recently, in cosmic terms, did dark energy overtake matter and the acceleration begin. The strange part is the timing. Of all the eras in the long life of the universe, we happen to live near the very crossover point, the moment when the two are roughly comparable and the balance tips. Why should we find ourselves at that special hinge in cosmic history, rather than long before or long after. No one knows whether this is a genuine clue or merely the way the numbers happen to fall. To pin down what dark energy really is, astronomers try to measure whether its push has stayed exactly constant through cosmic history or has changed. They do this with enormous surveys that map the three-dimensional positions of millions of galaxies, using the faint patterns in how galaxies are spaced as a ruler to measure the expansion at many different times in the past. If dark energy is a true constant, the expansion should follow one precise curve. If dark energy has shifted in strength, the curve bends differently. These surveys are among the most ambitious projects in astronomy, cataloguing galaxies by the millions across a large fraction of the sky. And it is exactly here that the recent cautious hints have appeared, faint suggestions in the data that dark energy might have been a little stronger long ago and be easing now. If those hints firm up, the simplest picture of a perfectly constant energy of the vacuum would be wrong, and the door would open to something more dynamic and stranger, with everything that implies for how the story ends. It is worth sitting for a moment with how completely this discovery overturned the expected story. For most of the 20th century, the great question about the fate of the universe was framed as a simple contest that gravity would ultimately decide. Either there was enough matter for gravity to halt the expansion and pull everything back, or there was not quite enough, and the expansion would coast outward forever, always slowing. Nobody's list of possibilities included the expansion speeding up, because nothing in the known inventory of the universe could do that. The accelerating universe was not a refinement of the old picture. It was a new ingredient that had been left out of every version of the story, an ingredient that turned out to be the majority of everything. To discover, in a single stroke, that more than 2/3 of the universe is a thing you had never accounted for, is a humbling event in the history of a science, and it happened within living memory. And it is in that 5% that the next mystery lives, because when we try to measure the very expansion that dark energy drives, our two best methods return two different answers, and neither side will give ground. Part 3. The two clocks that disagree. There is a single number that sits at the foundation of cosmology, and it measures how fast the universe is expanding. It is called the Hubble constant, named for Edwin Hubble, whose galaxies first revealed the expansion in the 1920s. The number tells you how quickly 2 points in space are drifting apart, and from it you can work out the age of the universe, its size, and much of its history. It is one of the most important quantities we measure, and right now we have a problem with it, one that has grown quietly into one of the sharpest disagreements in modern science. We have two excellent ways of measuring this number. They give two different answers, and both methods have become so precise that the gap between them can no longer be waved away as a mistake. To feel why this matters, imagine two very good clocks that are supposed to keep the same time. For a long while they were both a little blurry, and their readings overlapped enough that no one worried. But over the past decade, engineers on both sides polished their clocks until each one told time with tremendous confidence, and as the blur cleared, the two clocks were revealed to be reading differently. Not by much, but clearly and stubbornly, and by more than either side's stated precision should allow. When two careful measurements of the same thing refuse to agree, and neither will bend, physics takes notice, because it usually means something interesting is hiding in the gap. The first way of measuring the expansion reads it from the early universe, the oldest light in the cosmos, the faint afterglow left over from a few 100,000 years after the beginning, carries within it a detailed record of the young universe's contents and behavior. The Planck satellite, a European mission that mapped that ancient light with great care, read the expansion rate out of it. The value that comes from this early universe method is close to 67 kilometers per second per megaparsec. The units sound technical, but the idea is simple. For every step of distance you go out into the cosmos, the expansion carries galaxies away that much faster, and 67 is the size of that effect according to the early universe. The second way reads the expansion from the nearby present-day cosmos by building what astronomers call a distance ladder. You start with stars whose distances you can measure directly. You use those to calibrate a certain kind of pulsing star, called a Cepheid variable, which brightens and dims on a rhythm tied to its true brightness, so that its pulse tells you how far away it is. You use the Cepheids to calibrate the same Type 1a supernovae we met in the last mystery, which can be seen much farther out. Rung by rung, you climb from nearby stars to distant galaxies, measuring the expansion directly along the way. A collaboration known as the SH0ES team has done this measurement with enormous care. The value they get is close to 73. 67 and 73. Those numbers should be the same number. They are not. The difference is roughly 9%, which sounds small, but each side now claims a precision of 1 to 2%, and at that level, a 9% gap is a chasm. This disagreement has a name. It is called the Hubble tension, and it has refused to go away for years. If anything, as both measurements have improved, the tension has grown firmer, because the more precisely each side pins down its answer, the harder it becomes to blame the gap on ordinary error. So which side is wrong? That is exactly the question, and the honest answer is that we do not know, and it is possible that neither side is wrong in the ordinary sense. There are three broad possibilities, and cosmologists take all of them seriously. The first is that there is a subtle error somewhere in one of the measurement chains, some small effect that has been overlooked, most likely in the long ladder of the local method, since it has the most rungs and the most places to hide a mistake. Both sides have hunted for such errors relentlessly, checking and rechecking, and so far no error large enough to close the gap has been found. The second possibility is more interesting. Perhaps both measurements are correct, and the disagreement is telling us that our standard model of the universe is missing something between the early cosmos and now. The early universe method does not measure the expansion directly. It reads a value assuming that the universe behaved over billions of years exactly the way our current model says it should. If something happened in that history that the model leaves out, some extra ingredient in the young universe, then the early value would come out slightly wrong, even though the measurement itself was flawless. Proposed ingredients have names like early dark energy, a brief burst of extra pushing in the first fraction of the universe's life, or new kinds of the ghostly particles called neutrinos. Each of these can ease the tension on paper. None has been confirmed, and each brings problems of its own. The third possibility is simply that we do not yet understand our own measurements as well as we think, and that the resolution, when it comes, will teach us something we did not expect to learn. That is often how these standoffs end in physics. A disagreement that looks like an annoyance turns out to be a door. The most powerful new tool in the argument is the James Webb Space Telescope, which began its work only recently and can see the calibrating stars of the local method more clearly than any instrument before it. One of the first questions asked of it was whether the Cepheid stars at the base of the distance ladder had been measured correctly, or whether crowding and confusion in distant galaxies had thrown the numbers off. So far, the sharper view has not made the tension disappear. The local measurement has held up. The gap remains. It is worth appreciating what is really at stake here, beneath the technical language. The Hubble constant sets the scale of everything. It fixes how old the universe is, how large the observable cosmos is, and how the whole history fits together. A permanent, unexplained crack between our two best measurements of this number is not a small bookkeeping error. It is a flaw in the master clock of the cosmos, a sign that our timeline of the universe, which fits so much else so beautifully, has a fault line running through it that we cannot yet locate. Either we are making a mistake we cannot find, or the universe is more complicated than our simplest model allows. The pulsing stars at the base of the local ladder have a history worth telling because they are the reason the method works at all. Early in the 20th century, an astronomer named Henrietta Leavitt, studying photographic plates of the sky, noticed that a certain kind of star, the Cepheid variable, brightens and dims on a regular cycle, and that the length of the cycle is tied to the star's true brightness. A Cepheid that takes longer to pulse is genuinely more luminous. That single relationship turned these stars into cosmic mile markers. Find a Cepheid, time its pulse, and you know how bright it truly is. Compare that to how bright it looks, and you know its distance. It was Leavitt's discovery that let Edwin Hubble measure the distances to other galaxies in the first place, and it is the same kind of star that anchors the local expansion measurement today, a century later. From those pulsing stars, the ladder climbs rung by rung. The nearest stars have distances measured by simple geometry, by the way they appear to shift against the background as the Earth moves around the Sun. Those nearby stars calibrate the Cepheids. The Cepheids, visible in galaxies out to a certain range, calibrate the exploding stars, the same Type 1a supernovae from the dark energy story, which can be seen much farther still. Each rung is fixed to the one before it, and the whole ladder reaches from our own backyard to galaxies far out in the expanding cosmos. The strength of the method is that every step is checked against the next. The weakness is that a small error low on the ladder propagates all the way up, and with so many rungs, there are many places a subtle mistake could hide. This is why the local number has been scrutinized so relentlessly. To make sure the standoff is not an artifact of one particular technique, astronomers have brought in entirely independent ways of measuring the same expansion. One uses a different kind of aging star, the tip of the red giant branch, as an alternative to the Cepheids, sidestepping some of their difficulties. Another uses the way a massive galaxy can bend and delay the light of a distant flickering source behind it, timing the delay to gauge the expansion. Another still, one of the most elegant, uses the ripples in space produced when two dense stellar remnants spiral together and collide, events that act as what astronomers call standard sirens, because the shape of their signal reveals their true distance directly. These methods do not all agree perfectly with one another, and they carry their own uncertainties, but broadly, they tend to land nearer the higher, local value than the lower, early universe one. The tension has not dissolved under this variety of approaches. If anything, the fact that several independent local methods lean the same way has made it harder to blame any single technique. So the two clocks go on disagreeing, and the disagreement has become one of the defining problems of the field, argued over at every major gathering of cosmologists. Some suspect the answer will turn out to be a subtle, unglamorous error that, once found, quietly closes the gap and teaches us little. Others suspect the opposite, that the tension is the loose thread which, when pulled, unravels something we did not know was there, some missing ingredient in the young universe, or some new behavior of the very components, dark matter and dark energy, that we already could not explain. That is the reason a mere 9% discrepancy commands so much attention. In a science built on a precisely measured history of the cosmos, a permanent crack in the master clock is either a mistake we must find or a discovery we have not yet understood. There is a human texture to this standoff that is easy to miss in the numbers. Two large groups of careful scientists, using different instruments and different methods, have each measured the same quantity, about as well as it can be measured, and they have arrived at answers that will not reconcile. Neither group wants to be wrong, and both have gone to great lengths to prove themselves wrong and failed. That is the strange comfort of a good disagreement in physics. It is not two careless teams talking past each other. It is two careful teams who trust each other's work and still cannot make the sky agree, which is exactly the situation that tends to precede a real discovery. Whatever finally resolves the Hubble tension, whether a hidden error or a new piece of physics, it will have been earned by the refusal of both sides to look away from a number that would not behave. A disagreement about how fast the whole universe expands is unsettling enough. But some mysteries reach further back than that, to the question of why there is a universe here to measure at all. The next entry is about the narrowest survival in all of history, the reason there is something rather than nothing. Part 4. Why anything exists at all. Every particle of matter has a twin. For the electron, there is a particle with the same mass but the opposite charge, called the positron. For the proton, there is an antiproton. Physicists call these twins antimatter. and they are not science fiction. We make antimatter routinely in laboratories, and we understand it well. It obeys the same rules as ordinary matter, mirror reversed. There is only one dramatic thing about it. When a particle of matter meets its antimatter twin, the two annihilate completely, vanishing in a flash of pure energy. Matter and antimatter cannot coexist. Bring them together, and both are gone. Now hold that fact next to the story of the beginning. Our best understanding of the early universe says that in those first moments, energy was converting into matter, and the laws that govern that conversion are almost perfectly balanced between matter and antimatter. For every particle of matter created, an antiparticle should have been created too. The young universe should have contained matter and antimatter in equal amounts. And if it had, the story would have ended almost as soon as it began. Every particle would have found its twin, every pair would have annihilated, and the universe would have been left as an ocean of light with essentially no matter in it at all. No galaxies, no stars, no planets, no one to notice, just radiation, cooling forever in the dark. That is not what happened. You are here, the Earth is here, and the Sun, and every galaxy we have talked about. The universe is full of matter and contains almost no antimatter at all. Somehow, in the great annihilation of the early cosmos, matter won. And the question of how it won is one of the most fundamental unsolved problems in physics. It is, quite literally, the question of why there is something rather than nothing. The margin of victory was almost impossibly thin, and it is worth stating precisely because the precision is the wonder. The imbalance needed to explain our universe is about 1 part in a billion. That is, for roughly every billion particles of antimatter in the early universe, there were about 1,000,000,001 particles of matter. The billion pairs met their twins and annihilated, filling the cosmos with light. The single leftover particle out of each billion, the one with no twin to cancel it, survived. And that tiny residue, that 1 in a billion surplus, is everything, every galaxy in the sky, every atom in the earth, every cell in your body, is built from the matter that was left over after a near-total annihilation. We are the rounding error. We are what remained when almost everything cancelled out. The obvious question is what tipped the balance. If matter and antimatter were truly created in perfectly equal numbers, they would have annihilated perfectly, and nothing would remain. For a surplus of matter to survive, the laws of physics must not be perfectly even-handed. They must favor matter over antimatter, just slightly, by just about 1 part in a billion. The conditions that would allow this were worked out in 1967 by the Russian physicist Andrei Sakharov, who laid down the ingredients any successful explanation would need. His list is respected and clear. The problem is that when we look at the actual laws of physics as we know them, they do not provide nearly enough of the needed imbalance. The ingredients are there in trace amounts, far too small to explain a whole universe made of matter. We do know that matter and antimatter are not exactly mirror-perfect, because we have caught them behaving differently. In 1964, experiments with particles called kaons revealed a subtle asymmetry, a slight preference in the way certain particles decay, the first sign that nature is not perfectly balanced between matter and antimatter. This effect has a name, charge parity violation, usually shortened to CP violation, and it earned a Nobel Prize. Later experiments at particle accelerators found the same kind of asymmetry in heavier particles called B mesons. So the imbalance is real, and we can measure it. But when we add up all the CP violation we have ever observed, it falls dramatically short of what would be needed to leave behind the amount of matter we see. The known asymmetry is like finding a thumb resting lightly on one side of a scale when the scale is tilted far more than that thumb could possibly explain. Something much heavier is pressing down, and we cannot find it. This is not a fringe puzzle. It sits at the center of particle physics, and some of the most careful experiments in the world are built to chase it. Physicists trap antihydrogen, actual atoms of antimatter, and compare them to ordinary hydrogen with extraordinary precision, looking for any difference, however small, that might reveal why matter came out ahead. Others study neutrinos, the faint and abundant particles that stream through everything, because neutrinos have an unusual property. They may be their own antiparticles, and if they are, they could open a path to the imbalance that ordinary particles cannot. Long experiments are underway to measure whether neutrinos and their mirror versions behave differently, in the hope that the missing asymmetry has been hiding in the most elusive particles of all. For now, the accounting stands unbalanced in the most literal way. The universe is made of matter. The laws we know say it should have been made of equal parts matter and antimatter, which would have left it made of almost nothing. The gap between those two statements is our own existence, and we cannot yet explain what closed it. Every attempt to derive the 1 in a billion surplus from first principles comes up short. The reason there is a universe of substance, rather than a universe of empty light, is a question we can state with great precision and answer not at all. There is a quiet vertigo in this one, if you let it settle. Everything you have ever seen or touched, every person you have known, the ground under your feet and the stars overhead, all of it exists because of an imbalance of 1 part in a billion in the first instance of time, an imbalance that our deepest laws do not account for. We owe our entire reality to the narrowest of margins, preserved for reasons unknown. Antimatter is not a modern invention or a guess. It was predicted before it was found, which is one of the quiet triumphs of physics. In 1928, the British physicist Paul Dirac wrote down an equation describing the electron, and the mathematics insisted on a second solution, a particle just like the electron but with the opposite charge. Rather than dismiss it, Dirac took the equation at its word and proposed that such a particle must exist. 4 years later, in 1932, the American physicist Carl Anderson found it in the debris of cosmic rays remarkable, the atmosphere, a positive electron, exactly as the equation had demanded. The mirror twin of matter had stepped out of an equation and into the laboratory, and it has been part of physics ever since. Today, antimatter is almost ordinary in certain settings. Hospitals use it routinely. The scanning technique known as a positron emission tomography scan, a PET scan, works by detecting the tiny flashes of light produced when positrons from a specially prepared substance meet the ordinary electrons in a patient's body and annihilate. Every one of those flashes is a small enactment of the same process that shaped the early universe, matter and antimatter, meeting and vanishing into energy. The energy released is not trivial either. When a particle meets its antiparticle, their entire mass converts to energy, following the most famous relationship in physics, the equivalence of mass and energy. Gram for gram, it is the most complete release of energy that matter can undergo. This is exactly why a universe born with equal matter and antimatter would have emptied itself so thoroughly. Nearly all of it would have turned to radiation in that first great annihilation, leaving almost nothing behind. The search for what tipped the balance has driven physicists to imagine processes in the early universe far more exotic than anything we see today. One family of ideas looks to the moment when the fundamental forces were separating and the universe was passing through dramatic changes of state, hoping that in that turbulence, the laws briefly favored matter over antimatter by just the needed sliver. Another family, which has drawn growing interest, looks not to ordinary matter, but to neutrinos. If the heaviest, earliest neutrinos decayed in a lopsided way in the first instance, they could have seeded a small imbalance among lighter particles that eventually became the surplus of matter we see. This idea has an appealing feature. It ties the mystery of why matter exists to the strange, still unsettled properties of neutrinos, the most elusive particles we know, which may turn out to be their own antiparticles. That last possibility is why so much effort now goes into studying neutrinos with enormous, painstaking experiments. Physicists build detectors the size of buildings, filled with thousands of tons of material and buried far underground, to catch the faint interactions of these ghostly particles and to measure whether they and their mirror versions behave in exactly the same way or subtly differently. A confirmed difference would be a landmark, a possible thread leading back to the origin of matter itself. So far, the measurements are tantalizing but not conclusive, and the missing asymmetry remains missing. The universe is made of matter. Our laws say it should not be, and the reconciliation of those two statements is still one of the great unfinished tasks of physics. We are, quite literally, the residue of a near-perfect cancellation, and we cannot yet explain why the cancellation was not perfect. It is worth holding the scale of the annihilation in mind, because it makes the survival so much stranger. In the first fractions of a second, the young universe was filled with matter and antimatter in almost perfect balance, forming and annihilating constantly in a sea of radiation. As it cooled, the pairs met and vanished, converting themselves back into light, until nearly all of both were gone. If the balance had been exact, that would have been the whole history of matter, a brief flaring and then an empty, glowing cosmos. The 1,000,000,001 to a billion imbalance meant that when the great cancellation finished, a thin residue of matter had no antimatter left to meet, and so it endured. Everything solid in the universe, every star and world and living thing, is built from that thin residue, the one survivor in each billion, spared not by design that we can identify, but by an asymmetry our laws have not yet explained. We are, in the most literal sense, what the early universe could not quite cancel out. We exist because a faint signal survived the annihilation, a 1 in a billion whisper of matter that was never cancelled out. And fittingly, the next mystery is also a signal, one that arrives from across the universe in a few thousandths of a second, and vanishes before we can say for certain who sent it. Part 5. The Signals from Nowhere. Somewhere in the sky, for a few thousandths of a second, a single point flares in radio waves with an intensity that is hard to hold in the mind. In that instant, it pours out about as much energy as the sun releases over several days, and then it is gone, never to be seen from that spot again. These flashes are called fast radio bursts, and for years after the first one was found, astronomers could not say what caused them, where they came from, or even at first, whether they were real at all. They remain one of the most active mysteries in astronomy, and they arrive from staggering distances, letters flung across the observable universe in the blink of a recorder. The story begins in 2007 with a graduate student and an old archive. An astronomer named Duncan Lorimer, working with a student, was combing through data that the Parkes radio telescope in Australia had recorded back in 2001. Buried in that archive was a single spike, a burst of radio waves lasting only about 5,000ths of a second, unlike anything in the ordinary catalogue of the sky. It was so brief and so strange that many astronomers doubted it was real. Perhaps it was interference from Earth, a glitch, a stray signal from some human machine. The flash was nicknamed the Lorimer burst, and it sat under suspicion for years, a single unexplained blip that might have been nothing. Then more of them appeared. As radio telescopes improved and astronomers learned what to look for, the bursts turned up again and again, all over the sky, always brief, always intense. They were clearly real, and they were clearly not from Earth, because their light carried a specific fingerprint of distance. As a radio signal travels through the thin gas that fills space, its different wavelengths are slowed by slightly different amounts, so that the signal arrives smeared out in time, the higher frequencies reaching us a fraction of a moment before the lower ones. The amount of that smearing tells you how much space the signal has crossed, and the smearing on these bursts was enormous. They had not come from within our galaxy, they had come from far outside it, from across billions of light years. Consider what that means, and let it slow down for a moment. Picture a single burst on its way to us, far off, in a galaxy so distant that its light left before the Earth had formed. Something releases a pulse of radio energy in a few thousandths of a second. The pulse spreads out and races across the emptiness for billions of years, crossing the space between galaxies, passing through the thin gas of the cosmos, its short wavelengths pulling a hair ahead of its long ones the whole way. It crosses the edge of our own galaxy. It sweeps down through the dish of a radio telescope on Earth, and in the span of a single blink it registers, a faint chirp sliding from high notes to low, the compressed record of an immense journey, and then the sky is quiet again, as if nothing had happened. We are holding a letter that took billions of years to arrive, from a sender we cannot name, and it has already gone silent. For most of these bursts, that is all we get, a single flash, once, from a point in the sky, and never again. But a small number of them do something that cracked the mystery open a little. They repeat. One of these repeating bursts, catalogued as FRB 12102, flashed enough times that astronomers could watch the same spot and, eventually, pin down exactly where it lived. It was traced to a small, faint dwarf galaxy about 3 billion light-years away. For the first time, one of these signals had a return address. The burst was not a phantom in our own instruments. It was a real object, in a real galaxy, 3 billion light-years from here, doing something violent and repeating enough to be found. Still, knowing the address did not tell us the sender. What kind of object could produce such a thing? The answer, or at least a large piece of it, came from much closer to home, in April of 2020. A burst erupted from inside our own galaxy, close enough to study in detail, and its source could be identified. It came from a magnetar, catalogued as SGR 1935 plus 2154. A magnetar is a particular kind of neutron star, the collapsed core left behind when a massive star dies, packed so densely that a spoonful would weigh as much as a mountain. What makes a magnetar special is its magnetic field, which is among the strongest forces known anywhere in the universe, trillions of times stronger than the magnetic field of the Earth. When that field shifts and releases energy, the effects are extreme. And in 2020, one of them fired off a burst that looked for the first time like a fast radio burst produced right in our own neighborhood, from an object we could name. That was a genuine breakthrough. It linked at least some fast radio bursts to magnetars, and it gave the mystery a plausible engine at last. But it did not close the case, and here the honesty of the list returns. The bursts vary enormously. Some repeat with intricate structure, flickering in patterns. Most flash exactly once and never again. Some behaviors do not fit neatly with a single magnetar explanation. It may be that magnetars produce many of the bursts and other objects produce the rest. It may be that magnetars can make bursts in more than one way. The picture is genuinely unfinished, and new bursts are being caught faster than they can be fully understood. Thousands now catalogued, with dedicated telescopes sweeping the sky night after night. There is a lovely twist to the story that shows how a mystery can become a tool even before it is solved. Because each burst carries that fingerprint of all the gas it crossed on its way to us, astronomers realized they could use the bursts to weigh something else we had trouble finding. For years there had been a separate puzzle, a shortage of ordinary matter. Even setting aside dark matter, the normal atoms we could account for in stars and galaxies did not add up to the amount the early universe should have made. A good deal of ordinary matter seemed to be missing, presumably spread thinly in the space between galaxies where it was too faint to see. Fast radio bursts, passing through exactly that thin gas and recording it in their smearing, turned out to be able to measure it. The bursts helped find the universe's missing ordinary matter. A mystery we could not explain became an instrument for solving a different mystery entirely. So we are left with a strange and beautiful situation. We are receiving signals from across the observable universe, written in milliseconds by objects billions of light-years away, and we can now catch them by the thousands, weigh the cosmos with them, and trace a few of them to their home galaxies. And we still cannot fully say what they all are. We can read the envelope, the distance, the direction, the faint slide of the notes. We cannot yet read the hand of every sender. For a long time, the bursts were caught only by accident, one at a time, whenever a telescope happened to be pointed at the right patch of sky, at the right thousandth of a second. That changed with a new kind of instrument, a telescope built with no moving parts at all, staring at a wide band of the sky and letting the Earth's rotation sweep its view across the heavens, with banks of computers sifting the incoming data in real time for the telltale smear of a burst. Once telescopes like this came online, the trickle of discoveries became a flood. Bursts that had seemed rare and precious turned out to be happening across the sky constantly, perhaps hundreds or even thousands of times a day over the whole celestial sphere, most of them simply going unseen. The catalogue leapt from a handful to thousands in only a few years. The mystery did not shrink with the numbers, it sharpened, because now there was a whole population to explain, with all its variety. That variety is the core of the difficulty. Some bursts flash once and are never heard from again. Others repeat, returning to the same spot again and again over months and years. And at least one repeater startled astronomers by doing so on a rough schedule, going through stretches of activity and quiet in a cycle, as if something were turning toward us and away again. A source that flashes once looks like a catastrophe, a one-time event that destroys or exhausts whatever produced it. A source that repeats, especially on a rhythm, looks like something that survives its own outbursts and can fire many times. It is hard to see how a single kind of object could do both, which is part of why many astronomers suspect there is more than one cause, several different phenomena all producing brief, brilliant radio flashes by different means. The link to magnetars, forged by the burst from within our own galaxy in 2020, gave the field its firmest handhold, but the exact mechanism is still debated even for those. When a magnetar's fantastically strong magnetic field abruptly rearranges itself, it can release a colossal amount of energy, and somewhere in that violence a radio burst can be produced. But whether the burst comes from close to the star's surface or far out in the shock waves it launches, and whether all repeaters and non-repeaters share this engine, remains unsettled. Nature has shown us one clear example close to home, and left us to wonder how much of the distant population it truly represents. Even unsolved, the bursts have already earned their place as tools, and this is one of the more satisfying turns in the whole story. Because each burst's light is smeared by every wisp of gas it crosses, a burst is a kind of probe that has sampled the entire column of space between its home galaxy and Earth. By collecting many bursts at many distances, astronomers built a relationship between how far a burst has traveled and how much its signal was smeared, and that relationship let them weigh the thin gas spread through intergalactic space, the elusive ordinary matter that had gone missing from earlier accountings. The bursts found it, right where theory said it should be, hiding in the near emptiness between the galaxies. A phenomenon we cannot fully explain has been turned into a scale for weighing the universe, which is a fine reminder that in astronomy, a mystery is often a new instrument in disguise. There is something worth dwelling on in the timescales these bursts fold together. A fast radio burst lasts a few thousandths of a second, briefer than a blink, and in that sliver of time, it delivers an amount of energy that took its source ages to gather and release. Yet the journey between the release and our recording of it can span billions of years, longer than the Earth has existed, longer than the Sun. So each burst is a collision of the almost instantaneous and the almost eternal, a flash too quick to perceive that has been traveling since before there were oceans on this planet. When one of them registers on a telescope tonight, the event that produced it happened so long ago that the object responsible may have changed beyond recognition, or fallen silent, or ceased to exist. We are catching the light of an instant that ended before our world began, and calling it, quite rightly, news from the sky. Some of these signals we can at least place on the map, 3 billion light-years out, in a dwarf galaxy we can point to. But the next mystery is a flaw in the oldest signal of all, the light left over from the beginning of the universe, a photograph of the infant cosmos that carries a few blemishes we cannot explain. Part 6. The Flaws in the Afterglow. The oldest light in the universe is still arriving. It comes from every direction at once, a faint glow filling all of space, and it left its source about 380,000 years after the beginning, when the young cosmos had cooled just enough to become transparent for the first time. Before that moment, the universe was an opaque fog. After it, light could finally travel freely, and that first freed light has been streaming ever since, stretched by the expansion into faint microwaves. We call it the cosmic microwave background, and it is, in a real sense, a photograph of the infant universe. It is also one of the most precisely measured things in all of science, and for the most part it agrees with our theories to a degree that is almost uncanny. But there are a few features in this ancient photograph that do not sit quite right, and no one has fully explained them away. First, appreciate how smooth and perfect this light is, because the anomalies only stand out against that perfection. The cosmic microwave background sits at a temperature of about 2.725 degrees above absolute zero, the coldest temperature there is. And it is almost exactly the same in every direction, uniform to about 1 part in 100,000. If you could see in microwaves, the whole sky would glow with an even, featureless light, the same everywhere to a remarkable degree. It is the most perfect example of a certain kind of pure thermal glow ever found in nature. The tiny variations that do exist, differences of 100,000th of a degree from place to place, are the seeds from which all galaxies eventually grew, and their pattern matches theory beautifully. This is one of the great triumphs of cosmology, which is exactly why the handful of oddities matter. The first oddity is a place in the southern sky known as the cold spot. Among the tiny temperature variations across the sky, one region stands out as unusually large and unusually cold, colder than the ordinary statistics comfortably allow. It is not that a cold region should not exist at all. Random variation produces warmer and cooler patches everywhere, and that is expected. It is that this particular patch seems too big and too cold to fit easily into the expected spread. One proposed explanation is that a truly enormous underdense region lies between us and that part of the sky, a supervoid, a stretch of space with fewer galaxies than average, which could subtly chill the light passing through it. Careful searchers have looked for such a void, with mixed and debated results. Another explanation is simpler and less satisfying. It might just be a rare fluctuation, an unlikely but possible roll of the cosmic dice. Neither answer has settled the matter. The second oddity is stranger still, and it goes by a memorable nickname, the axis of evil. The name is dramatic, but the effect is subtle, and it has nothing to do with anything sinister. It refers to an apparent alignment. When astronomers look at the largest scale patterns in the ancient light, the broadest ripples spread across the whole sky, those patterns seem, faintly, to line up along a particular direction in space. This is peculiar, because the universe on the largest scales is supposed to have no preferred direction at all. Every direction should be equal. There should be no cosmic arrow, no special axis. And yet the biggest features in the oldest light seem to point, however faintly, somewhere in particular. It may be a coincidence, the kind of accidental alignment that can happen by chance when you only have one sky to look at. It may be a subtle contamination from something in the foreground, some nearby source leaking into the measurement. Or it may be a genuine hint of something about the early universe that our theories do not include. What makes both of these anomalies hard to dismiss is that they have survived repeated, independent measurement. 3 great missions have mapped the cosmic microwave background over 3 decades, each far more precise than the last. The COBE satellite first measured the tiny temperature variations in the early 1990s. The WMAP mission mapped them in far greater detail in the 2000s. And the Planck satellite produced the most exquisite map yet in the 2010s. Each of these missions confirmed the overall triumph, the near-perfect glow and the seed pattern that grew into galaxies. And each of them, looking carefully, still saw the cold spot and the strange alignment. The anomalies did not wash out with better data. They persisted, quietly, across every attempt to measure them more precisely. Here the honest limits of the science are sharp, and they are unusual. The trouble with these anomalies is that we have exactly one universe to examine and exactly one sky. If you flip a coin 10 times and get an unusual streak, you can flip it another 10 times and see whether the streak was a fluke. We cannot re-roll the cosmos. We cannot take a second photograph of the infant universe from a different vantage, because there is only the one, seen from the one place we stand. So we may never be able to fully separate a genuine signal from a rare accident. A pattern that would be meaningful if we could repeat the experiment may be forever ambiguous because the experiment cannot be repeated. That is the quiet disquiet of this mystery. The clearest photograph we will ever have of the young universe, a picture of astonishing perfection that confirms so much of what we believe, carries a small number of blemishes that we cannot explain and cannot test again. They may be nothing, they may be everything, and it is the one image we can never retake. To understand what we are looking at, it helps to know what that moment 380,000 years after the beginning actually was. Before it, the universe was hot enough that atoms could not hold together, electrons roamed free, and light could not travel far without being scattered, so the cosmos was an opaque, glowing fog. As the universe expanded and cooled, it crossed a threshold where electrons could finally settle onto nuclei to form the first stable atoms, and in that instant the fog cleared. Light that had been trapped was at last free to fly, and it has been flying ever since. The cosmic microwave background is that first freed light, and the pattern frozen into it is a snapshot of the universe at the exact moment it became transparent. When we study the anomalies, we are studying tiny irregularities in that single, ancient photograph. The cold spot is not the only feature that raises eyebrows, though it is the most famous. There is also a faint suggestion that the sky is not quite the same on opposite halves, a subtle lopsidedness in the strength of the ripples from one side to the other, which is odd in a universe expected to look statistically the same everywhere. And the very largest ripple of all, the broadest possible variation across the sky, comes in a little weaker than the standard picture predicts, as though the universe were slightly quieter on its grandest scales than it should be. Individually, each of these is modest. Collectively, they form a small cluster of features that, taken together, keep a corner of cosmology mildly uneasy. The great difficulty in judging them is a trap that scientists know well and guard against, the trap of noticing a pattern only after it appears and then being impressed by it. If you scan a huge sky full of random ripples, you are almost guaranteed to find some patch that looks unusual somewhere, simply because there are so many places to look. The honest question is not whether an odd feature exists, but whether it is odder than random chance should produce across the whole sky. For the cold spot and its companions, that question has been argued carefully for years, and the answer sits frustratingly in the middle. The features are unusual enough to be worth noticing, but not so unusual that chance can be ruled out, and with only one sky to examine, we may never be able to push past that ambiguity. It is the rare situation in science where more data cannot fully help, because there is no more data to be had. There is one universe, one photograph, and a few blemishes we will likely always be arguing about. There is a deeper reason these small anomalies are taken seriously rather than shrugged off, and it has to do with how much rests on this one image. Nearly everything we claim to know about the composition and age of the universe is read, in part, from the fine details of this ancient light. The proportions of ordinary matter, and dark energy, the age of the cosmos, the flatness of space, the pattern of the seeds that grew into galaxies. All of it is extracted from the ripples in the afterglow, and the extraction works with astonishing precision. So when a few features in that same image sit slightly outside expectation, the stakes are higher than they first appear. If the anomalies are mere chance, the triumphant picture stands untouched. If they are real, they are a whisper that the model which explains so much may still be missing a line, somewhere in the earliest chapter of all. That is why astronomers keep returning to a handful of faint blemishes in a picture that is, by every other measure, one of the great successes of science. A flaw in the picture of the infant universe leads naturally to a puzzle about what that young universe went on to build. because in those early times, the cosmos assembled objects so large, so quickly, that we still cannot account for how they were finished in time. Part 7. The Giants That Grew Too Fast. At the center of nearly every large galaxy sits a black hole of almost incomprehensible size. Not the kind left behind when a single star dies, which might weigh a few times as much as the Sun, but something far larger, weighing millions or even billions of times the mass of the Sun. These are the supermassive black holes, and they anchor the galaxies around them. Our own Milky Way holds one, called Sagittarius A star, weighing about 4 million suns, sitting quietly at the galactic center. How these giants formed at all is a hard question, but the mystery that keeps astronomers awake is sharper than that. We keep finding them fully grown at times when the universe was far too young to have built them. To feel the problem, you have to think about how a black hole grows. A black hole gets bigger by swallowing matter, pulling in gas and stars, and merging with other black holes. But there is a natural speed limit to this feeding. As matter falls toward a black hole, it piles up and heats up and glows fiercely, and that glow pushes outward on the gas still trying to fall in. Feed too fast, and the black hole's own brilliance blows away its next meal. This limit means a black hole cannot simply gorge without restraint. It grows at a bounded pace, doubling its mass only over a long stretch of time. Start from an ordinary seed, a black hole a few times the mass of the Sun left by a dying star, and there is only so large it can become in a given number of years. Now put that speed limit next to what we actually see. Astronomers have found quasars at the edge of the observable universe, so far away that we are seeing them as they were when the cosmos was less than 1 billion years old, a small fraction of its present age. A quasar is the blazing core of a galaxy where a supermassive black hole is feeding voraciously, shining so brightly that it can be seen across almost the entire universe. And these early quasars already contain black holes of 1 billion solar masses or more, 1 billion times the mass of the Sun, fully assembled when the universe had barely begun. Start from a star-sized seed at the earliest possible moment and feed it at the maximum allowed rate the entire time, and you still struggle to reach 1 billion solar masses that fast. The giants are there before the arithmetic says they can be. The James Webb Space Telescope has sharpened the puzzle, rather than easing it. Peering back to the first few 100 million years of cosmic history, it has found black holes that are not only present remarkably early, but also strangely large compared to the galaxies that host them. In the nearby universe, there is a tidy relationship. A galaxy and its central black hole grow together, and the black hole ends up a small fraction of the mass of all the stars around it. But some of these very early systems break the pattern. Their black holes are enormous relative to their meager surrounding starlight, as if the black hole got a head start the stars never had. The recipe that built the modern relationship does not seem to have been followed in the beginning. So how did nature make such giants so quickly? There are two leading ideas, and both are plausible, and neither is confirmed. The first is that the earliest black holes did not start from ordinary star-sized seeds at all. Instead, in the special conditions of the young universe, enormous clouds of gas may have collapsed directly into black holes of tens of thousands of solar masses in one step, skipping the star stage entirely. Starting from such a heavy seed, the climb to 1 billion solar masses becomes far easier to finish in time. The trouble is that forming such a direct collapse seed requires conditions that are difficult to arrange, and we have not yet caught one in the act. The second idea is that the early universe allowed brief episodes of feeding faster than the usual limit. Perhaps, in the denser conditions of the young cosmos, matter could pour into a black hole in bursts that outran the ordinary breaks, letting it pack on mass in surges. This too is possible in principle, and this too has not been shown to actually happen at the required scale. It may be that both ideas are partly right, heavy seeds and fast feeding working together. It may be that we are missing something else entirely. What we can say plainly is this: the largest gravitational engines in the cosmos, the supermassive black holes that anchor galaxies and shape their surroundings, were already running at full size when the universe was in its infancy. We can measure them, we can weigh them, we can see them blazing as quasars near the very beginning of cosmic time. And we cannot fully explain how they were built so fast. The blueprint is missing a step, and every improvement in our telescopes, rather than filling in that step, has so far only shown us the finished giants sitting there earlier and larger than before. The speed limit on a black hole's feeding is not an arbitrary rule. It comes from a tug of war the black hole wages against itself. As matter spirals inward, it heats up and blazes with light, and that light pushes outward on the gas still falling in. Feed slowly, and gravity wins, and the black hole grows. Feed too fast, and the outpouring of light shoves the next meal away before it can be swallowed, and the growth stalls. There is a natural balance point between these two, a maximum sustainable rate, and it sets how quickly a black hole can double its mass. Working through the arithmetic, a black hole growing at that steady maximum roughly doubles over a span of tens of millions of years. Start from a seed a few times the sun's mass, and to reach 1 billion suns you need to double again and again, many times over, and the total time that requires is close to, or even longer than, all the time the early universe had available. Quasars themselves have been known since the 1960s, when astronomers found star-like points of light that turned out to be the blazing cores of distant galaxies, so luminous that they outshine all the stars around them combined. As telescopes reached farther, they found quasars at greater and greater distances, which means further and further back in time, and the record holders now sit within the first several 100 million years of cosmic history, already powered by black holes of many hundreds of millions to billions of solar masses. The James Webb Space Telescope has added a population of small, intensely red points of light in the early universe, which appear to harbor growing black holes that are startlingly heavy compared to the modest galaxies around them. Whatever built these objects, it worked fast, and it worked early, and it seems to have built the black hole ahead of the galaxy rather than alongside it. This is why the idea of heavy seeds has drawn so much attention. If in certain special pockets of the young universe, a large cloud of gas could collapse straight into a black hole of tens of thousands of solar masses without first fragmenting into ordinary stars, then the long climb to 1 billion suns would have a running start and could plausibly finish in time. The conditions required are delicate. The gas must be kept from cooling and fragmenting into stars, perhaps bathed in enough light from neighboring regions to stay smooth as it collapses. Whether nature actually arranged such conditions, and how often, is unknown. Others have wondered whether black holes might have formed directly in the extreme densities of the very first instance of the universe, long before any star existed, providing seeds of their own. Each idea is workable on paper, and none has been caught happening. The giants are there, earlier and larger than the simple arithmetic allows, and the recipe that finished them in time is still missing a crucial line. There is a broader lesson hiding in these early giants, and it is a recurring one in this field. Almost every time we have built a more powerful telescope and pointed it further back in time, expecting to catch the universe in a simpler, more primitive state, we have instead found things more mature and more assembled than we predicted. Galaxies that formed sooner than the models allowed. Heavy elements present earlier than they should be, and now black holes already grown to enormous size when the cosmos had barely begun. The pattern suggests that the early universe was a more productive and faster working place than our theories expected, building large structures on a timescale we have not fully accounted for. Each of these surprises has eventually been folded into an improved understanding, but the black holes remain among the most stubborn because the speed limit on their growth is rooted in physics we trust. The giants were there too soon, and explaining how remains genuinely open. There is a quiet grandeur to it. These objects now sit mostly still, like the one at the center of our own galaxy, feeding little, giving off almost nothing, having done their violent growing long ago. They are settled elders of the cosmos, whose youth we cannot reconstruct. And yet even now, the universe has not lost its capacity to startle us with things that seem to come from nowhere. Because every so often, it fires a single particle at us, carrying the energy of a thrown ball, launched by an accelerator we have never been able to find. Part 8. The particle that should not exist. On the night of October 15, 1991, an instrument in the Utah desert recorded a single particle so extreme that physicists gave it a name usually reserved for exclamations. They called it the "Oh my God" particle. It was a proton, one of the ordinary building blocks of matter, but it was moving with an energy that has no business belonging to something so small. In a single subatomic particle, billions of times smaller than a grain of sand, it carried roughly the energy of a baseball thrown at a brisk pace, the kind of throw you could easily catch across a yard. All of that energy packed into one proton, arriving out of the sky. To understand why this is so strange, it helps to know what cosmic rays ordinarily are. Space is full of fast-moving particles, mostly protons, streaming from the sun and from more distant sources, constantly remarkable the top of Earth's atmosphere. Most of them are unremarkable, but a rare few arrive with energies so far beyond the ordinary that our best ideas about cosmic accelerators strain to explain them. The "Oh my God" particle was the most extreme ever recorded, carrying tens of millions of times more energy than the most powerful particle accelerator humanity has ever built can produce. We spend billions of dollars and build machines many kilometers around to push particles to high energies. Nature did far better by an enormous margin with a single proton, and sent it to us for free. Consider the moment it arrived. It is a clear night over the Utah desert. High above the ground, at the very top of the atmosphere, a single proton traveling at almost exactly the speed of light strikes an atom of air. In that instant it shatters into a spray of new particles, and each of those strikes more air and shatters again, and in a fraction of a second, a single unimaginably fast proton has bloomed into a cascade of billions of particles raining down over a wide patch of desert. The detectors on the ground catch the edge of that rain, a brief glow spreading across the sky's floor, and from it, the physicists reconstruct the one particle that started it all, arriving from somewhere out in the darkness, announcing itself in a shower of light, and then leaving nothing behind but a number almost too large to believe. That proton was moving so close to the speed of light that the gap is hard to write down in ordinary terms. If you raced a beam of light and that proton across the galaxy, the light would win by only the tiniest sliver, a difference so small it takes many decimal places to express. For all practical purposes, it was moving at the speed of light itself, and yet it was a massive particle, not a massless ray. Nothing we know of on Earth, and few things anywhere, can push a proton that hard. And here the mystery sharpens into something genuinely puzzling, because physics says particles like this should be rare, not only because they are hard to make, but because they should struggle to reach us even if they are made. There is a predicted ceiling on the energy of cosmic ray protons that travel long distances, called the GZK limit, named for the three physicists who worked it out. The reasoning is elegant. Space is filled with the faint microwave glow left over from the early universe, the same ancient light we discussed earlier. A proton moving with extreme energy, plowing through that glow over millions of light-years, should occasionally collide with those microwave photons and lose energy in the process, bleeding off its extreme speed until it drops below the ceiling. So a proton arriving above that ceiling cannot have traveled very far. It must have come from somewhere relatively nearby in cosmic terms. But when astronomers trace the arrival directions of these highest energy particles back to their sources, they find a problem. The sky in those directions often looks empty. To accelerate a particle to such energies, nature needs an engine of staggering power, a jet from a supermassive black hole, the shock waves of colliding galaxy clusters, the blast of an exploding star. These are the few things violent enough to do the job. And yet the arrival directions frequently point toward patches of sky where no such powerful engine sits close enough to fit the GZK reasoning. The particle should have come from nearby, and nearby there is nothing obvious that could have made it. the "oh my God" particle was not a one-time fluke. In 2021, a detector recorded another particle of comparable extraordinary energy, and it was given the name Amaterasu, after a sun goddess. Like its predecessor, it arrived from a direction where no clear, powerful source could be found. Two of these near-impossible particles, decades apart, both seeming to come from empty sky. Either there are hidden accelerators we have not identified, or the particles are somehow reaching us from farther away than the GZK limit should allow, or something about our understanding of these extreme energies is incomplete. So the honest picture is this. Every so often, the universe fires a single particle carrying the punch of a thrown ball across the emptiness of space, launched by a mechanism we cannot identify, arriving from a direction that appears to hold nothing capable of launching it. These particles are real. We have caught them, and we cannot yet say what built the gun. It is a reminder that even the empty-looking sky holds engines we have not found, quietly hurling fragments of matter at us across distances we can barely comprehend. These particles are so rare at the highest energies that catching them requires detectors spread across enormous areas of ground. At the very top of the energy scale, only about one such particle strikes each square kilometer of the Earth in a century, which means that to catch a meaningful number, you must watch a huge stretch of land for years. So physicists have built sprawling observatories, arrays of detectors dotted across hundreds or thousands of square kilometers of desert and plain, patiently waiting for the rain of particles that a single extreme cosmic ray produces when it shatters against the top of the atmosphere. One enormous array sits in the plains of Argentina. Another watches the desert of Utah, where the "oh my God" particle was first caught. Between them, they have recorded the handful of the most energetic particles ever known. Tracing these particles back to their birthplaces is maddeningly hard for a reason beyond the empty-looking sky. Space is threaded with faint magnetic fields, and a charged particle traveling through a magnetic field is bent from its path. Over the immense distances involved, even weak magnetic fields can curve a proton's trajectory, so that the direction it arrives from is not quite the direction it came from. The particle's memory of its origin is smeared by every field it crossed. Only at the very highest energies, where the particles are so stiff that the magnetic fields barely deflect them, is there any hope of pointing back toward a source, and even then the pointing is rough. This is part of why the arrival directions are so puzzling. When astronomers do look toward where the most energetic particles seem to originate, they sometimes find a faint excess from one broad region of sky, a suggestion of a hotspot, but no single obvious engine bright and close enough to satisfy the strict distance limit. The candidates for what could accelerate a particle to such energies are all among the most powerful objects known. The jets launched by supermassive black holes at the centers of active galaxies, where matter falling in is flung back out at nearly the speed of light. The shock waves where entire galaxy clusters collide. The birth cries of the most extreme collapsed stars. Any of these could, in principle, act as a natural accelerator dwarfing anything humanity could build. The trouble is matching a specific particle to a specific source, given the smearing of magnetic fields and the emptiness in the traced directions. So the extreme cosmic rays remain a standing puzzle, a reminder that the universe contains engines of a violence we can measure by their products, without being able to point to the engines themselves. To feel the energy of one of these particles in more familiar terms, hold two pictures side by side. On one side, a subatomic proton, so small that trillions upon trillions of them would fit in a grain of sand, a thing we normally measure in the faintest whispers of energy. On the other side, a baseball crossing a yard at the speed of a gentle throw, something you could catch in your hand without a thought. The extraordinary fact is that the single proton and the thrown ball carry roughly the same energy of motion. All the energy of a tossed ball concentrated into one particle almost inconceivably smaller than a speck of dust. That is what arrived over the Utah desert on that October night, and what arrived again decades later from another empty patch of sky. The universe found a way to load a thrown ball's worth of energy onto a single proton and fling it across the cosmos. and we still cannot point to the arm that threw it. A single particle from an unseen source is startling enough on its own, but it points toward a larger and stranger question, one that touches every mystery on this list. Why is the universe set up to allow any of this at all? Why do its basic numbers sit exactly where they need to sit for stars and atoms and observers to exist? Part 9. The numbers that are too perfect. The laws of physics come with a set of numbers attached. The strength of gravity, the mass of the electron, the strength of the force that binds the centers of atoms together, the amount of dark energy woven into space. These numbers are not predicted by any deeper theory we possess. We do not derive them. We simply go out and measure them, write them down, and use them. And when physicists ask a simple question about these numbers, the answer is quietly unsettling. What would happen if the numbers were slightly different? For a great many of them, the answer is that a universe with almost any other settings would be lifeless, and often would have no structure at all. The window of values that permits stars, planets, chemistry, and observers appears, on the numbers, to be narrow. Take the strong nuclear force, the force that holds the centers of atoms together. If it were a few % weaker, the simplest heavy atoms would not hold, and the chemistry that life depends on could not assemble. If it were a few % stronger, the balance of nuclear reactions that let stars shine steadily and forge the elements would tip, and the ordinary matter of the universe would come out wrong. Either way, a small change and the familiar periodic table never fills out. Or take dark energy, the mystery from earlier on this list. If it were much larger than it is, space would have flown apart so fast in the early universe that gravity could never have gathered matter into galaxies at all. There would be no galaxies, no stars, no planets, just thinning gas racing into the dark. The observed value is fantastically small, and it sits almost exactly where it needs to sit for structure to form. The example that most captures the strangeness of this involves the element carbon, and a prediction made in 1953 by the astronomer Fred Hoyle. Carbon is the backbone of all known life, and it is forged inside stars, built up step by step from lighter elements. Hoyle realized that for stars to make carbon in the amounts we see, the carbon nucleus needed to have a very specific property, an energy level positioned in just the right place to let the reaction proceed. No one had measured such a level. Hoyle argued it had to exist, essentially because we are here, made of carbon, and the universe is full of the stuff, so the reaction must work. He predicted the exact property required, sent experimenters looking for it, and they found it, right where he said it would be. It stands as one of the boldest predictions in the history of physics, made on the reasoning that the universe must be capable of producing the very physicists asking the question. Now, one might hope that all these apparent tunings trade off against one another, that if you nudged one number the wrong way, you could nudge another to compensate and rescue the universe. Sometimes that is partly true, but remarkably, several of these numbers each independently rule out complexity when changed on their own. It is not one delicate setting on a single dial. It is a handful of separate dials, each of which, turned too far, gives you a universe with no atoms, or no stars, or no structure. The tunings do not all lean on one another. Several stand alone. So why do the constants sit where they do? Here, the honest list gives its plainest answer yet. We do not know. There is no accepted explanation for why the numbers of physics have the values they have. What we have instead is a set of serious ideas, none of them proven, and each of them pulls in a different direction. The first idea is the multiverse. Suppose that our universe is not the only one, that there are a great many universes, perhaps unimaginably many, each with its own settings of the constants. In most of them, the dials are turned to lifeless values, and nothing complex ever forms, and no one is there to notice. But in a rare few, the dials happen to land in the narrow window that allows stars and chemistry and observers. We necessarily find ourselves in one of those rare few, not because ours was chosen, but because it is the only kind of universe in which askers can exist. This is called the anthropic argument, and it turns the fine-tuning from a miracle into a selection effect. Its weakness is equally clear. We have no direct evidence of any universe other than our own, and it is genuinely difficult to test. The second idea is almost the opposite. Perhaps there is a deeper theory we have not yet discovered, a more fundamental layer of physics that fixes all these numbers uniquely so that they could not have been anything other than what they are. On this view, the fine-tuning is an illusion born of our ignorance. The numbers only look freely adjustable because we do not yet know the rule that sets them. Find the rule, and the apparent coincidence dissolves. The weakness here is that no such theory has been found, and some of our best attempts to build one have, if anything, pointed back toward enormous numbers of possible universes rather than a single fixed answer. The third idea is a caution about the question itself. Perhaps the sense of fine-tuning is partly an artifact of how we are reasoning. We imagine turning the dials freely, one at a time, and we are impressed by how bad most settings are. But maybe that picture of independent, freely turned dials is misleading. Maybe the numbers are related in ways we do not grasp, or maybe our very notion of what counts as a life-permitting universe is too narrow. On this view, the mystery is real, but our framing of it may be flawed, and part of the work is learning to ask the question correctly. All three remain live. None has won, and that is the remarkable thing to sit with. The same universe that will not explain its own dark energy also set that number, and several others, precisely where galaxies could form, where stars could burn, where carbon could be forged, and where the atoms that make up the listener could come to exist. Whether that is chance selected out of countless universes, or a law we have not found, or a question we have not learned to ask properly, the honest answer is that we do not know. The universe permits us, exquisitely, and it will not tell us why. The carbon story deserves a closer look, because it is the clearest single case of the whole puzzle. Inside a star, carbon is not made in one step, but by a delicate three-part reaction. Two helium nuclei must first stick together into an unstable, fleeting pair, and then, before that pair falls apart, a third helium nucleus must strike it to form carbon. This is a narrow chance at best. What makes it work at all is that the carbon nucleus happens to have an energy level positioned almost exactly where it is needed to catch the reaction on the way through, giving it a resonance, a matching note that lets the three pieces come together far more readily than they otherwise could. Fred Hoyle reasoned that this level had to exist, because otherwise stars could not have filled the universe with carbon, and we, made of carbon, would not be here to wonder about it. He was right. Nudge that energy level even modestly, and the universe would be starved of carbon, and the chemistry of life would have no foundation. The list of finely balanced quantities goes further, and each one is independent. The difference in mass between the neutron and the proton is tiny, but it sits in just the right place. Tilt it a little one way, and the proton would be unstable, and matter as we know it could not persist. Tilt it the other, and stars could not burn as they do. The strength of gravity compared to the other forces is set so that stars form, live for billions of years, and die at a stately pace. Make gravity much stronger and stars would burn out in a rush. Make it much weaker and they might never ignite. Even the fact that space has 3 dimensions rather than 2 or 4 appears to matter, because stable orbits and stable atoms are far easier to arrange in 3. Several of these settings, adjusted on their own, each independently close the door on a universe of structure and life. It is not one lucky number. It is a handful of them, each landing in a narrow band. This is what gives the multiverse idea its pull, however uncomfortable it is. If the universe we live in is one of an immense number, each with the dials set differently, then the overwhelming majority would be sterile and empty, and only a rare few would land in the life-permitting band. We would necessarily find ourselves in one of the rare hospitable ones, not because it was arranged for us, but because those are the only kind in which anyone can be around to look. Some versions of this idea grow naturally out of theories in which the early universe kept sprouting new regions endlessly, each potentially settling into different physics. an image touched on in an earlier video about the beginning of things. The difficulty is testability. A universe causally cut off from ours, that we can never see or reach, sits at the very edge of what science can address, and thoughtful physicists disagree about whether invoking it explains anything or merely relocates the mystery. The honest position holds all the possibilities loosely. Perhaps a deeper theory will one day show that the constants could not have been otherwise, and the fine-tuning will look, in hindsight, like a question we asked before we understood the answer was fixed all along. Perhaps the multiverse is real, and our hospitable universe is one lucky draw among countless failures. Perhaps the whole framing of dials we imagine turning freely is subtly mistaken. What cannot be denied is the observation at the center of it. The same universe that will not explain its own dark energy also set that number, and several others, exactly where galaxies could gather, stars could burn steadily, carbon could be forged, and the atoms of a listener could assemble. That is either the deepest coincidence in existence or the deepest clue, and we do not yet know which. There is a temptation, when facing numbers this finely balanced, to leap to a comfortable conclusion in one direction or another, and the honest path resists both leaps. It is tempting to treat the tunings as proof of purpose, and it is equally tempting to wave them away as meaningless, because we are, after all, here to observe them. Careful physicists try to do neither. They hold the observation at arm's length and ask what it would take to explain it without assuming the answer in advance. That restraint is why the fine-tuning problem has stayed a serious scientific question rather than drifting into slogans. The numbers are real, their narrowness is real, and the explanation is genuinely unknown. What makes this entry belong on a list of mysteries is not that it hints at any particular answer, but that it poses a precise question our physics cannot yet address about why the universe's own settings permit the existence of anyone able to measure them. It is a question that sits at the boundary between physics and something larger, and thoughtful people who agree on every measurement can still disagree, reasonably and permanently, about what it means. That disagreement is not a weakness in the science. It is an honest sign that we have reached a real edge, a place where the facts are firm and the interpretation is still open, and where the wisest stance is to keep the question in view without pretending to have closed it. If the numbers really are tuned so finely in our favor, we might expect to find ourselves at the center of things, important, noticed. And yet the next mystery is the opposite feeling entirely. It is the discovery that our entire galaxy is being carried across the universe, quietly and steadily, toward a mass we can barely see. Part 10. What is pulling the Milky Way? We tend to think of our galaxy as sitting still, turning slowly in place while the universe drifts by outside it. That is not what is happening. The Milky Way, together with the whole crowd of galaxies around it that we call the local group, is being pulled through space at a great speed toward a particular region of the sky. We are moving at roughly 600 kilometers per second in a specific direction, which is faster than almost anything you will ever hear described, fast enough to cross the distance from the Earth to the Moon in about 10 minutes, and much of whatever is doing the pulling is hidden from us, blocked from view behind the body of our own galaxy. The motion was pieced together in the 1970s and 80s as astronomers carefully mapped how galaxies move across the sky. Galaxies do not simply ride the general expansion of the universe outward. On top of that expansion, they drift toward concentrations of mass, tugged by gravity toward wherever matter has gathered most thickly. When astronomers charted these drifts across our part of the cosmos, they found that many galaxies, including our own, are streaming together toward a common region, in the direction of the southern constellation Centaurus. Something massive sits that way, and it is pulling a whole neighborhood of galaxies toward it. They named it the Great Attractor. Here the trouble begins, and it is a peculiar kind of trouble. The direction of the Great Attractor lies close to the plane of the Milky Way itself, in a band of sky that astronomers call the zone of avoidance. This is the region blocked by the dust and stars of our own galaxy, the bright, crowded stripe of the Milky Way that we cannot easily see through. So for decades, we were in the strange position of being pulled towards something we could barely observe, because our own galaxy stood squarely in the way. We could feel the tug in the motion of galaxies, and we could point roughly toward its source, but the source itself sat behind a curtain we could not part. As instruments improved, especially those that can peer through dust using other wavelengths of light, more of the picture came into view. The Great Attractor turned out to be a genuine concentration of galaxies and mass, but it was not the whole story. Beyond it, farther in the same general direction, lies an even more massive concentration called the Shapley supercluster, one of the largest gatherings of galaxies in the nearby universe. Part of our motion seems to be a pull toward the Great Attractor, and part of it a pull from the greater mass of Shapley beyond. We are being drawn not toward a single object, but toward the accumulated gravity of an enormous region of the cosmos. In 2014, astronomers gave this whole arrangement a shape and a name. By mapping the motions of thousands of galaxies and tracing which way they all stream, a team defined the boundaries of our home supercluster, the giant structure to which the Milky Way belongs. They named it Laniakea, a Hawaiian word meaning immense heaven. Laniakea contains something like 100,000 galaxies and stretches across roughly 500 million light-years. Within it, all the streaming motions, including our own 600 kilometers per second, flow along toward a common region, like water running down the slopes of an enormous basin toward its lowest point. It is a beautiful and humbling picture, our galaxy as one droplet in a flow of 100,000 galaxies, all sliding together across 500 million light-years. And yet, even with this grander map, the accounting is not fully closed. When astronomers try to add up all the visible mass in the direction we are heading, it is debated whether it is quite enough to explain the full speed and direction of our motion. Some of the pull may come from even more distant concentrations, beyond the parts we have mapped well. There was also, for a time, a bolder and more controversial claim that a large collection of galaxy clusters seemed to be streaming coherently toward one direction across a truly enormous stretch of the universe, a motion that was nicknamed dark flow. Whether that larger bulk motion is real or an artifact of difficult measurements has been argued back and forth and is not settled. The safe statement is the modest one. We are being carried across the cosmos by gravity, toward mass we can only partly see, and we have not yet fully counted what is doing the pulling. There is something quietly moving in this mystery, different from the others on the list. It is not about a distant particle or an abstract number. It is about us, all of us, everything we are, being carried steadily across the universe toward a place we cannot clearly see, at a speed no rocket will ever match, and we did not even notice until we learned to measure it. The ground is not still. The galaxy is not still. We are in motion, always have been, toward the immense heaven of Laniakea, drawn by a weight behind a curtain. We know we are moving with real confidence, and the way we know is elegant. The ancient light of the cosmic microwave background is supposed to look the same in every direction, but it does not quite. On one side of the sky, it appears very slightly warmer, and on the opposite side, very slightly cooler. And this small imbalance is not a property of the light itself. It is the fingerprint of our own motion. Because we are moving through the universe, the light ahead of us is nudged toward the warm end, and the light behind us toward the cool end, the same way a moving listener hears a shift in a steady tone. From the size of that warm and cool imbalance, astronomers can read off our speed and direction with precision, and the answer is that the whole local group is sweeping along at roughly 600 kilometers per second toward that region near Centaurus. Our motion is written into the oldest light in the sky. Piercing the curtain of our own galaxy to see what lies behind it has been slow, patient work. Using wavelengths of light that penetrate dust better than visible light does, astronomers have gradually mapped the hidden region and found real structures there, clusters of galaxies that had been lurking behind the bright band of the Milky Way all along. As recently as the last decade, entirely new concentrations of galaxies have been discovered in these obscured zones, gatherings large enough to influence the flows of their neighbors, which had simply never been catalogued because our own galaxy stood in front of them. Each such discovery fills in a little more of the map in the direction we are traveling, and each helps account for a little more of the pull, though the full sum is still being tallied. The larger claim, the one that remains genuinely contested, concerns whether there is a coherent motion on scales even greater than Laniakea. Some studies, examining the movements of galaxy clusters across very large volumes, reported that they seemed to be streaming together toward one direction more than the standard picture of the universe would predict, a bulk motion that was given the evocative name dark flow. If real, it might hint at the pull of enormous structures beyond the edge of what we can survey, or at something stranger still about the largest scales of the cosmos. But measurements on scales this enormous are extraordinarily difficult, and other studies have found the effect to be weaker or absent, consistent with ordinary expectation. Whether dark flow is a real feature of the universe or an artifact of hard measurements is not settled. What is certain is the humbler and stranger fact that we are in motion, always, carried by gravity toward the immense heaven of Laniakea, and still counting the weight behind the curtain. There is a shift in perspective that this mystery quietly demands, and it is worth pausing on. We are used to imagining the Earth as the moving thing, and the galaxy as the fixed backdrop, and beyond that, in our mind's eye, the universe as a still stage on which everything else happens. But there is no still stage. The Earth moves around the Sun moves around the center of the galaxy, carrying the whole solar system on a long orbit that takes hundreds of millions of years to complete. The galaxy itself moves within its local crowd. And the entire crowd is streaming, at 600 kilometers every second, toward the immense heaven of Laniakea, and whatever mass lies beyond it. There is no anchor anywhere, no fixed point to measure everything else against, only motion within motion within motion, all the way up. When you lie still tonight, you are not still at all. You are being carried across the universe, as you always have been, toward a destination we can only partly see. We are moving toward something, carried by the great flows of the cosmos. But every so often, the reverse happens. Every so often, something moves toward us, a visitor from another star, passing through our small corner of space before vanishing back into the dark. And not long ago, for the first time, we caught one in the act. Part 11. The Objects Passing Through. On October 19, 2017, a telescope in Hawaii called Pan-STARRS caught something moving across its images that had never been confirmed before. It was a faint point of light, small and easy to miss, but its path was wrong in a very particular way. It was moving too fast and along a track too steep to belong to our solar system. Everything born with the Sun, every planet, asteroid and comet, orbits in loops that keep it bound to the Sun's gravity. This object was not on a loop. It was on a path that could only mean one thing. It had come from another star, fallen briefly through our solar system, and was already on its way back out into the space between the stars. It was the first confirmed interstellar visitor ever seen, and it was given the name Oumuamua, a Hawaiian word meaning a scout, or a messenger reaching out from the distant past. Oumuamua was small, only a few hundred meters across, and by the time it was found it was already leaving, having made its closest approach to the Sun weeks earlier. That left astronomers a narrow window to study it before it faded beyond reach, and in that short time it behaved strangely enough to start arguments that have not ended. The first strange thing was its brightness, which swung up and down dramatically as it tumbled through space. The pattern of that swing suggested a bizarre shape, an object far longer than it was wide, possibly like a cigar, or perhaps like a flattened disk. Nothing in our own asteroid belt looks quite like that. Whatever it was not a shape we see nearby. Picture the encounter as it actually was. A faint dot slides across the telescope's frames, night after night, moving against the fixed stars. It is already outbound, already pulling away from the Sun and gaining speed as it goes. It tumbles as it travels, and because its shape is so uneven, its brightness rises and falls in a slow rhythm, bright when its long side faces us, dim when it turns edge on. Astronomers race to point every available instrument at it, because they know the window is closing by the day. It is small and faint and receding, and there is no spacecraft anywhere that could be sent to catch it in time. We watch it the way you might watch a stranger's car pass on a distant road at night, knowing you will never learn who was driving, only that they came from somewhere far away and are already gone. The second strange thing was the most debated. As Oumuamua left the inner solar system, it sped up slightly more than the sun's gravity alone could account for. There was an extra push, small but measurable, carrying it away a little faster than gravity predicted. Now, there is a familiar explanation for such a push. Comets do exactly this. As a comet nears the sun, its ices warm and turn to gas, and the venting gas acts like a gentle thruster, nudging the comet off its purely gravitational path. But comets that vent this way grow a visible tail, a glowing cloud of gas and dust. Oumuamua showed no such tail. It accelerated as if something were pushing it, without the visible sign that normally comes with that push. Most astronomers favor a natural explanation, that it was venting gases we rarely see, ices of a kind that release without producing an obvious tail. A minority argued that the anomaly was unusual enough that we should keep an open mind about what it was, rather than assume the ordinary answer. What almost everyone agrees on is that we ran out of time to settle it. By the time the questions were sharp, Oumuamua was already too far away to examine, and no answer could be forced. Then something happened that put the whole episode in perspective. In 2019, only 2 years later, an amateur astronomer named Gennady Borisov, observing with a telescope he had built himself, spotted a second interstellar object. This one was catalogued as 2I Borisov, and it was different in a reassuring way. It looked, in almost every respect, like an ordinary comet, the kind we know well, except that it too was on an unbound path that marked it as a visitor from another star. It had a tail. It behaved as a comet should. Where Oumuamua had been strange and ambiguous, Borisov's comet was familiar and clear. Two visitors, arriving within 2 years of each other, with two completely different characters, one odd and hard to explain, one perfectly recognizable. That contrast is itself instructive. It tells us that interstellar objects are not all alike, and that the first one we saw was not necessarily typical. What both of them together made clear is that these visitors are out there, passing through, more often than we ever realized. For most of history we had no way to catch them. They are small and fast and faint, and by the time they are noticed, they are usually already leaving. But new surveys, with telescopes designed to scan the whole sky repeatedly, are expected to find many more in the coming years, perhaps regularly. Each one is a physical sample from another star system, a genuine piece of somewhere else, drifting through our own. And there is a growing hope that one day we might be ready in advance, with a spacecraft prepared to launch on short notice, to fly out and meet the next strange visitor while there is still time to look closely. For now, the honest summary is a wistful one. For the first time in history, we watched a fragment of another star system fall through our own and pass on by. We saw it, measured it, argued about it, and then it left, before we could answer even the simplest questions about what it was and where exactly it had come from. It is a mystery defined as much by lost opportunity as by the object itself. A reminder that the universe sometimes offers us a single, brief look and then closes the door. The object was such a genuine first that the world's astronomers had to invent a new category for it. Until then, every small body ever catalogued belonged to the Sun. Now there was one that plainly did not, and it was given a designation marking it as the first interstellar object ever recorded. A new class opened with a single entry. Its formal name and its Hawaiian name, Oumuamua, both carry that sense of a first contact with something from beyond, a scout arriving from the distance and passing on. Almost everything about it had to be pieced together from that swing in brightness, because it was too small and too far to photograph as anything but a point of light. The brightness rose and fell by a large factor over a few hours, and the most natural way to produce so extreme a variation is an object that is very elongated or very flattened, turning end over end so that it presents now a broad face and now a narrow edge. That is how the early estimates of a cigar-like or pancake-like shape arose, and either would be unusual because nothing in our own neighborhood tumbles with quite that profile. Its motion was not a tidy spin either, but a slow, complex tumble, the kind of end-over-end wobble an object settles into after some past disturbance. Its color was faintly reddish, a tint common on surfaces that have been weathered by long exposure to cosmic radiation, consistent with something that had drifted between the stars for a very long time. The natural explanations for its extra push have grown more inventive as astronomers have tried to account for an acceleration without a visible tail. One proposal is that it was a fragment of frozen nitrogen, a shard chipped from the icy surface of a world in another star system, venting nitrogen gas too clear to see easily. Another is that it was made partly of frozen hydrogen, or that it was an extraordinarily fluffy, porous object, so lightweight and airy that even the faint pressure of sunlight could nudge it measurably. Each idea explains part of the behavior and strains on some other point, and none can be confirmed, because the evidence left the solar system with the object. What the debate really revealed is how little a single brief encounter can settle, and how much we would have given for just a few more weeks of close observation. That is the lesson the astronomers took most seriously, and it is shaping what comes next. New sky surveys, using large telescopes designed to scan the entire visible sky over and over, are expected to catch interstellar visitors far earlier and far more often, perhaps turning a once-in-history event into a regular occurrence. And there is a growing effort to be ready in advance, with spacecraft that could be held in waiting and dispatched on short notice to fly out and meet the next strange visitor while it is still close enough to study. If that readiness pays off, then some future object like Oumuamua might not slip away unexamined. We might next time get to look it in the face before it returns to the dark. For now, the first one remains the one that got away, seen clearly enough to know it was extraordinary and lost before we could learn what kind of extraordinary it was. The two visitors together taught a quiet lesson about how easily we generalize from a single example. When Oumuamua appeared, it was the only interstellar object anyone had ever confirmed, and so every strange thing about it felt like it might be telling us what such objects are like in general. Then the comet from another star arrived, ordinary in almost every way, and the picture widened at once. One sample is not a population. The truth is that interstellar objects are probably as varied as the star systems that make them, some icy and familiar, some strange and hard to classify, and we happen to meet an odd one first. As the new surveys begin to catch them regularly, we will finally be able to speak of interstellar visitors as a class with a range of characters, rather than guessing at the whole from a single fleeting encounter. Until then, the first scout remains both our introduction to a new kind of object and a caution against reading too much into any one of them. A lone object passed through and vanished, leaving us wondering about the star that made it. But that wondering has a larger and older form, the deepest version of the question. If pieces of other star systems drift through ours, what about the systems themselves? In a galaxy of hundreds of billions of stars, across more than 13 billion years, is anyone out there? And if so, why have we heard nothing? Part 12. The Great Silence. The galaxy is old and enormous. It has been turning for more than 13 billion years, and it holds somewhere between 100 and 400 billion stars. We now know that most of those stars have planets, because we have found thousands of them, and the count keeps climbing, and that planets like the Earth, at the right distance from their star for liquid water, are common. So here is the setup. Hundreds of billions of stars, countless worlds, more than 13 billion years of time. If life arises with any regularity at all, and if even a small fraction of it ever becomes capable of sending a signal or spreading between the stars, then the galaxy should show some sign of it. Given the numbers, Given the time, someone should have left a trace. And yet, when we look and when we listen, we find nothing certain. The sky is silent. This is the puzzle we call the Fermi paradox, and it was distilled into a single question over lunch in 1950 by the physicist Enrico Fermi. In the middle of a casual conversation about the sheer size of the galaxy and the likelihood of other civilizations, Fermi is said to have asked, simply, "Where is everybody?" The question has stayed with us ever since, precisely because it is so hard to answer. The galaxy is old enough and large enough that even a slow, patient spread of life across it should have reached everywhere long ago. Even faint radio signals, leaking out from other worlds over millions of years, should be detectable somewhere. The expectation and the observation do not match. That mismatch is the paradox. To think about it clearly, astronomers use a framework written down in 1961 by Frank Drake, now called the Drake equation. It is not really an equation that gives an answer. It is a way of organizing our ignorance, dividing the big question into a chain of smaller ones. How many stars are there? What fraction have planets? How many of those planets are suitable for life? On how many suitable planets does life actually begin? On how many of those does life become intelligent? How many intelligent species develop the ability to signal across space? And crucially, how long do such civilizations last and keep signaling before they fall silent? Multiply the chain together, and you get an estimate of how many detectable civilizations should be out there right now. The difficulty is that only the first term, the number of stars, is well measured. Every term after that is deeply uncertain. Choose hopeful values for each, and the galaxy should be busy with voices. Choose cautious ones, and we might be the only ones here. The same equation supports both a crowded galaxy and an empty one. Depending on numbers we simply do not know. The proposed resolutions are many, and the serious ones are sober rather than sensational. Perhaps life itself is extraordinarily rare, and the step from lifeless chemistry to the first living thing almost never happens, so that living worlds are scattered thinly across enormous distances. Perhaps life is common, but intelligence is the rare step, and most living worlds never produce anything that builds a telescope. Perhaps the rare step is survival, that civilizations capable of signaling tend to be short-lived, undone by their own troubles or by natural catastrophe before they can spread or endure. This last idea has a name that captures the unease around it, the Great Filter, some barrier in the long chain from simple chemistry to a lasting galactic presence that almost nothing gets past. The unsettling question is where that filter sits. If it lies behind us, in some improbable early step we already cleared, then we may be rare and largely alone, but safe. If it lies ahead of us, in some challenge no civilization has yet survived, then the silence is a warning. There are gentler possibilities too. Perhaps the others are out there and simply do not broadcast, listening rather than shouting, or communicating in ways we do not know how to detect. Perhaps we have not been listening long enough, or on the right frequencies, or in the right way. The organized search has a name, the search for extraterrestrial intelligence, and it has been underway in various forms since 1960, sweeping the skies for a signal that stands out from the natural noise of the cosmos. In all that time, there has been one moment that still refuses to be explained. In August of 1977, a radio telescope in Ohio recorded a strong, narrow signal that lasted 72 seconds and then was gone. It was so remarkable on the printout that the astronomer reviewing it wrote a single word beside it, "Wow," and by that name it has been known ever since. The wow signal has never been satisfactorily explained by any natural source, and it has also never repeated, despite many attempts to catch it again. One clean, strange note heard once from the direction of the stars, and then silence. Let the shape of that silence settle for a moment, because it is the real subject of this mystery. Earlier on this list, we described a fast radio burst as a letter arriving from across the universe, from a sender we could not name. Here the image returns, but changed. The letters we most hope to receive, the ones that would tell us we are not alone, may simply never have been sent. Or their senders may be long gone, their signals still crossing the emptiness, ages after the ones who made them have vanished. When we listen to the galaxy, we are listening across not just distance but time, and the silence we hear could mean many things. It could mean there is no one. It could mean there was someone, once, and we have missed them. It could mean they are there now and we have not yet learned how to hear. The silence itself is the only data we have, and no one agrees what it is telling us. There is something in this that reaches every person who has ever looked up on a clear night and felt the size of the sky. In a galaxy of hundreds of billions of stars, across more than 13 billion years, we have so far heard nothing that we can be sure came from another mind. Whether that means we are alone, truly and finally alone, or whether it means only that we are early, among the first to arrive and the first to listen, is a question that touches all of us. Both answers are quiet, both are humbling, and we cannot yet tell which one we are living inside. The organized listening began in earnest in 1960, when Frank Drake, the same astronomer who would later write the famous equation, pointed a radio telescope at two nearby sun-like stars and listened for any signal that stood out from the natural hiss of the cosmos. He heard nothing conclusive, but he had started something. In the decades since, the search has widened enormously, sweeping across more stars, more of the sky, and a broader range of radio frequencies, with ever more sensitive receivers and ever faster computers to sift the torrent of data for anything that looks deliberate. Modern efforts scan millions of stars and enormous stretches of the radio spectrum, and still, across more than 60 years of listening, there has been no confirmed signal from another civilization, only the natural voices of the universe, and once, that single unexplained note in Ohio. Part of what makes the silence hard to interpret is the sheer size of the haystack. A civilization could be broadcasting on any of an enormous range of frequencies, in any direction, in bursts or steadily, in forms we might not even recognize as artificial. We have listened to a great deal, but compared to all the possible combinations of frequency, direction, and time, our total search so far has been likened to dipping a single glass into the ocean and finding no fish. An empty glass does not prove an empty sea. This is the strongest version of the gentle resolutions to the paradox. Perhaps the others are there, and we simply have not yet listened long enough, or broadly enough, or in the right way, to hear them. But the harder resolutions cannot be waved away, and they are where the real weight of the question lies. The idea of the great filter sharpens them into a single unsettling choice. Somewhere along the enormous chain from lifeless chemistry to a lasting, galaxy-spanning civilization, there may be one or more steps that almost nothing gets past. A filter that keeps the galaxy silent by keeping the chain from ever completing. The unsettling part is not that the filter exists, but that we do not know where it sits. If the filter is behind us, in some fantastically improbable early step, the origin of life itself, perhaps, or the leap to complex cells, then we may be among the very few to have cleared it, rare and largely alone, but with the hard part already behind us. If instead the filter lies ahead, in some challenge that every technological species reaches and none survives, then the silence is a warning about our own future, written in the emptiness of the sky. The same data, the same silence, supports both a hopeful reading and a sobering one. There are gentler stories too, and they are worth holding alongside the stark ones. Perhaps advanced civilizations do not broadcast at all, having learned to listen rather than shout, or communicating by means we have not discovered. Perhaps they are long-lived but quiet, spread thinly, uninterested in announcing themselves. Perhaps the distances are simply so great, and the windows of overlap in time so narrow, that two civilizations almost never happen to be listening toward each other at the same moment across the ages. In a galaxy that has existed for over 13 billion years, a civilization that signals for even a few thousand years is a candle lit for a single heartbeat in a very long night, and two such candles, lit in different rooms at different moments, might never see each other's light. Let that image settle, because it is the true subject here. when you stand under a clear night sky and let your eyes adjust until the faint stars come out, you are looking at hundreds of billions of suns, most of them circled by worlds, spread across a galaxy so old it defeats the imagination. And out of all of that, across all of that time, we have heard, with certainty, nothing. No greeting, no accidental leakage, no unmistakable sign that another mind has ever looked back. Whether that means we are truly alone, the only ones who ever woke up in this galaxy, or whether it means only that we are early, among the first to arrive and the first to listen, is a question that reaches past astronomy and touches something personal in everyone who has ever felt small under the stars. Both answers are quiet. Both change how you see the sky, and we cannot yet say which one is true. One more thought belongs here, because it changes how the silence feels. When we listen to a star 1,000 light-years away, we are not hearing it as it is tonight. We are hearing it as it was 1,000 years ago, because that is how long its light and any signal riding with it took to reach us. Extend that across the galaxy, and our survey of the sky is not a snapshot of the present at all, but a layered record of many different pasts, each star reported to us at a different age. A civilization could arise and signal, and fall silent entirely within the time its light has been crossing the gap to us, so that we would receive its first broadcast long after it had ended. Listening across the galaxy is listening across time as much as space, and the silence we hear is assembled from countless different moments in the long history of a galaxy far older than the Earth. That is part of why the silence is so hard to read. It is not one silence. It is a chorus of silences from 1,000 different pasts, and somewhere inside it the answer is hiding. Whether we are alone or merely early, the objects that might one day hold the answer are still objects we do not fully understand. We have talked about the black holes that anchor galaxies, but the deepest question about them is not how they formed. It is what happens to everything that falls in, a question that pits our two greatest theories of physics against each other. Part 13. What happens to what falls in? A black hole is a place where gravity has become so strong that nothing can escape it, not even light. It has a boundary, called the event horizon, which marks the point of no return. Cross it, and there is no path back out, because escaping would mean moving faster than light, and nothing can do that. For a long time, this seemed to be the entire story for anything unfortunate enough to fall in. It was gone, sealed away forever, behind the horizon, beyond all reach and all knowledge. Then, in 1974, a young physicist named Stephen Hawking showed that the story could not be that simple, and in doing so, he opened one of the sharpest and most stubborn conflicts in all of modern physics. Hawking's discovery was that black holes are not perfectly black. When you carefully combine the physics of the very small, quantum mechanics, with the behavior of empty space near the edge of a black hole, something subtle happens. The black hole slowly leaks a faint radiation, now called Hawking radiation, drifting away from just outside the horizon. And because it is losing energy this way, a black hole is not eternal. Over time it shrinks. Given long enough, it evaporates entirely, fading away until nothing is left. The timescales involved are almost beyond meaning. A black hole formed from a dying star would take vastly longer than the current age of the universe to evaporate, so long that the number is written with dozens of digits. But the direction is clear. Black holes are not permanent vaults. They leak, and they die, and eventually they are gone. That result, beautiful as it is, created a genuine crisis, and to see why you have to understand one of the deepest rules in quantum physics. In quantum mechanics, information is never truly destroyed. The precise details that describe any object, the exact arrangement that makes it what it is, are always preserved in principle. You could burn a book to ash, and in the smoke and heat and light, the information about that book would, in principle, still be there, scrambled beyond any practical hope of recovery, but never actually erased. The universe, at its most fundamental level, does not forget. This is not a minor technicality. It is woven into the mathematical core of the theory, and physics does not work without it. Now put the two ideas together and watch them collide. Throw a book into a black hole. The information about that book crosses the horizon and is lost to us. But that seemed acceptable as long as the black hole lasted forever, holding the information sealed inside. Hawking showed that the black hole does not last forever. It evaporates, slowly turning into that faint radiation. And here is the problem. Hawking's original calculation said that the escaping radiation is featureless, the same bland glow regardless of what fell in, carrying none of the details of the book. So when the black hole has fully evaporated and vanished, where did the book's information go? If it is truly gone, then quantum mechanics is wrong, because the universe has forgotten something it is not allowed to forget. If it is not gone, then it must have escaped somehow, and Hawking's own calculation did not show how. This is the black hole information paradox, and it sets our two greatest theories, gravity and quantum mechanics, directly against each other. Each works flawlessly in its own domain. Here, at the edge of an evaporating black hole, they cannot both be right as written. For decades, this problem has been one of the central battlegrounds of theoretical physics, and the emerging consensus, hard-won and still incomplete, is that the information probably does escape. It is not truly lost. Somehow it is encoded in the outgoing radiation after all, written into subtle correlations that Hawking's first calculation missed. The strongest ideas about how this works come from a surprising direction, a principle called holography. The holographic principle suggests that everything happening inside a region of space can be fully described by information living on its boundary, as though the interior were a projection of data stored on the surface that encloses it. Applied to a black hole, this hints that the information about everything inside is somehow also present on the horizon, available to be carried away as the black hole evaporates. In recent years, theorists working with new mathematical tools, involving structures they call islands, have made real progress in showing how the books can balance, how the information can come back out in a way that respects quantum mechanics. But progress is not the same as resolution, and the honesty of the list holds here as everywhere. Even if the information does escape, the question of exactly how it physically gets out remains genuinely unsettled, and the answer seems to demand strange things about the inside of a black hole. If information is to escape, some of our comfortable assumptions about what the region near the horizon is like may have to give way. There have been fierce debates about whether an astronaut falling in would pass smoothly through an unremarkable horizon, as the older picture said, or whether something more violent and strange waits there instead. The fact that our best theories cannot agree on what it would be like to cross the boundary of a black hole tells you how unfinished this remains. Even Hawking himself changed his mind over the long course of the argument. Having first concluded that information was lost, he later came to accept that it probably is not, and at one point conceded a famous friendly bet he had made with another physicist on exactly this question. It is a small human detail in an abstract problem, but a telling one. The person who found the paradox spent much of the rest of his life wrestling with it, and revised his own answer as the understanding deepened. So the fate of everything that has ever fallen into a black hole, every star, every cloud of gas, every particle drawn past the horizon since the universe began, remains a live question. Not because black holes are exotic curiosities, but because answering it means reconciling the two theories that underpin all of physics, the physics of gravity and the physics of the very small, which everywhere else keep politely to their own domains and here are forced into open disagreement. When we finally understand what a black hole gives back, we will understand something far larger than black holes. One of the strangest and most beautiful results to come out of this work is that a black hole behaves as though it has a temperature, and with it, a kind of hidden disorder that can be counted. In the years around Hawking's discovery, physicists realized that the amount of hidden information a black hole contains is measured not by its volume, as you might expect, but by the area of its horizon, the surface of the sphere marking the point of no return. Double the surface area, and you double the black hole's capacity to hide information. This was a genuine surprise, because everywhere else in physics the amount a region can hold scales with its volume, its interior, not with the area of its boundary. A black hole seemed to store its secrets on its surface. That single clue, that the information capacity lives on the boundary rather than in the interior, became one of the most important hints in all of theoretical physics, and it pointed toward a radical idea about how reality is put together. That idea is the holographic principle. It proposes, in its boldest form, that everything happening within a volume of space can be completely described by information living on the surface that encloses it, as a flat hologram can encode a full three-dimensional scene. If that is right, then the inside of a black hole is not a separate sealed world at all, but something fully captured by data on its horizon. Data that could, in principle, be carried away by the escaping radiation as the black hole evaporates. The information would not be trapped forever after all. It would be written on the surface the whole time, waiting to be released. This turned the paradox from a dead end into a research program, and over the following decades it grew into one of the richest areas of theoretical physics, connecting black holes to the most fundamental questions about how space and gravity themselves might emerge from something more fundamental. The debates along the way have been fierce and revealing. At one point, physicists argued over whether an astronaut falling into a black hole would pass through the horizon without noticing anything special, as the smooth older picture said, or whether the demands of preserving information might require something violent and strange waiting at the boundary instead, a wall of high-energy particles. The very fact that our best theories could not agree on what it would feel like to cross the edge of a black hole showed how far the confusion ran. More recently, using powerful new mathematical tools, theorists have made real progress in showing how the escaping radiation can carry information out in a way that respects quantum mechanics, tracking exactly how the balance of information shifts as a black hole evaporates, and confirming that it can, in principle, all come back. These are landmark steps, but they are steps in a calculation, and translating them into a clear physical story of how a specific book's information physically threads its way out of a specific black hole remains unfinished. What keeps this problem at the center of physics is that it is not really about black holes. It is about the seam where our two greatest theories meet and fail to agree: gravity, which governs the large and the heavy, and quantum mechanics, which governs the small, work flawlessly in their own domains and almost never have to confront each other directly. A black hole is one of the rare places where both matter at once, where something extraordinarily heavy is also governed by quantum rules, and there the two theories are forced into open conflict over a simple question with a definite answer. Resolving that conflict fully would mean uniting gravity and quantum mechanics into a single, deeper theory, the long-sought goal that has eluded physics for a century. So the fate of what falls into a black hole is not a curiosity at the edge of science. It is a doorway to the theory beneath all the others, and we are still working out how to walk through it. It is worth appreciating how ordinary the ingredients of this paradox are, because that is what makes it so sharp. There is nothing exotic in the setup. A black hole, which we now observe routinely and even photograph. A rule that information is preserved, which underlies all of chemistry and computing and every prediction quantum theory makes. And a slow leak of radiation, derived from physics we trust. Each piece, on its own, is solid and well tested. It is only when you put all three together and follow them honestly to the end that they produce a contradiction. And the contradiction will not go away by discarding any one piece, because none of them can be spared. That is the mark of a genuine crisis in physics, as opposed to a mere puzzle. It is not that we are missing a fact. It is that our most trusted ideas, each correct in its own domain, cannot all be correct at once in the one place where they are forced to meet. The resolution, when it is finally complete, will not just explain black holes. It will tell us which of our certainties needed to bend. If even a black hole must eventually surrender what it swallowed, giving it back to the universe over unimaginable spans of time, then it is worth asking the last and largest version of that question, Not what a single black hole gives back, but what the whole universe gives back. How does all of this end? Part 14. How it all ends. Every list of the universe's mysteries arrives, in the end, at the same place, the ending itself. How does the cosmos finish? And the honest answer carries a strange symmetry, because the fate of everything turns almost entirely on the two things we understood least at the very start of this list, the invisible 95%, and above all on dark energy. Change the nature of dark energy even slightly, and you change the end of everything. The first mystery we discussed, and the last, are in truth the same mystery, seen from opposite ends of time. What decides the future of the universe is the very component we still cannot name. The leading picture is the one that follows if dark energy stays roughly constant, exactly as the simplest description says it might. It is called the Big Freeze, and it is sometimes given the plainer name heat death. In this future, the universe expands forever, and it slowly runs down. The process is gentle and unimaginably long. Galaxies gradually use up the gas from which stars are made, and as that gas is spent, fewer and fewer new stars are born. The existing stars burn through their fuel and die, the largest first, the smallest last. The small, cool red stars are so frugal that they will go on shining for trillions of years, long after the brighter stars have gone dark. But even they run out eventually, and when the last of them fades, the universe enters a long twilight populated only by the dead remnants of stars, the white dwarfs slowly cooling, the neutron stars, and the black holes. Let that far future settle into view for a moment. Imagine standing in a galaxy an almost meaningless span of time from now, when the last star is guttering out. The sky is not full of light, it is nearly empty of it. The bright river of stars overhead has gone dark, one by one, over spans so long the numbers stop carrying meaning. What remains drifts in a cold quiet, the burned-out cinders of suns, giving off less and less warmth. Even the black holes, the last great structures left, do not endure forever, because, as we saw, they slowly leak their energy away, and over spans beyond any counting, evaporate into a faint whisper of radiation. And then, even that fades. The universe settles toward a still, cold, thinly spread sameness, a state in which nothing is hot and nothing is cold, nothing is dense and nothing is empty enough to build from, a condition where no new event can happen because every difference that could drive a change has been smoothed away. Not an explosion, not a collapse, a long, complete forgetting. There is a particular kind of peace in that picture, if you meet it the right way. Heat death is not a catastrophe in the ordinary sense. Nothing is destroyed in violence. The universe simply comes to rest, the way a long day comes to rest at its end, everything winding gently down until there is nothing left to do but be still. It is the closing of a very great distance, and to sit with it is to feel something like acceptance, the calm of letting go of a thing that has run its full and complete course. But the big freeze is only the ending we get if dark energy behaves itself, and dark energy is exactly the thing we cannot yet trust to behave. There are other endings, and each of them hangs on what this one unnamed component decides to do. If dark energy strengthens over time, growing more powerful as the universe ages, then the expansion does not merely continue, it runs away, it accelerates without limit, until the push of dark energy overwhelms every force that holds things together. First, it would pull apart the great clusters of galaxies. Then, growing stronger, it would tear apart individual galaxies, then unbind the stars from one another, then rip apart the planets, and at the very end, in the final moments, it would pull apart the atoms themselves. This ending has a name, the Big Rip, and unlike the slow twilight of heat death, it is a tearing, a coming apart of all structure, decided entirely by whether dark energy keeps its strength or gathers more. There is another possibility that runs the opposite way. If, instead of pushing forever, the expansion someday reversed, then everything would begin to fall back together. The galaxies would draw closer, the cosmos would grow hotter and denser, and the universe would rush toward a hot, crushing finale, a mirror of its fiery beginning. This ending is called the Big Crunch, and some have wondered whether such a collapse might not be a true end at all, but a turning point, a moment where a crushed universe rebounds into a new expansion, a big bounce, beginning the whole story over again. This is a question explored in an earlier video, the idea of a beginning that grows out of an ending, and it remains genuinely open. And there is one more possibility, the strangest and quietest of all, which does not depend on dark energy, but on the nature of empty space itself. It is conceivable that the vacuum of space, what looks like perfect emptiness, is not actually in its lowest possible energy state. If that were true, then somewhere, someday, a tiny patch of space could drop to that lower state, and the change would spread outward at the speed of light, rewriting the laws of physics inside an expanding bubble as it went. This is called vacuum decay, and its unsettling feature is that it would give no warning, because it would arrive at the very speed of the light that might have carried word of it. It is almost certainly not something to fear in any human sense, on any timescale that touches us. But it is the deepest reason that the far future cannot be fully guaranteed, a reminder that even the emptiness may hold a change we cannot rule out. Which ending is ours? Here we arrive at the honest core of the whole list, and it is fitting that the final answer is the same as the first. We do not know. And that is not a failure. We cannot say how the universe ends, because we still cannot say what dark energy is, and dark energy holds the pen. Recent hints that its strength might not be perfectly constant, the very hints we mentioned near the beginning, keep every one of these endings on the table. The big freeze, the big rip, the big crunch, the possibility of a bounce, the distant chance of vacuum decay, all of them remain live, because all of them wait on a single unanswered question about the largest and most invisible thing in the cosmos. And so the list closes where it opened, on the 95% of the universe we have never seen. We began with the missing mass that holds galaxies together, and the mysterious force that drives them apart, and we have traveled outward through disagreeing measurements and stray signals, through impossible giants and single particles, through numbers too perfect, and a silence too complete, and we have come at last to the ending of everything, only to find the same two unseen things waiting there to write it. The fate of the universe is authored by exactly the mysteries we understood least when we started. Every question on this list is honestly open, and each one is open in the same way, at the careful edge of a map we keep drawing a little further into the dark. It is worth walking, slowly, through the long twilight of the big freeze, because the eras of the far future have a strange and calming grandeur when you lay them out in order. We live now in what might be called the age of starlight, the era of shining suns, and it feels permanent, but on the true scale of the future, it is only the brief opening chapter. Star formation will continue for a long while yet, but the gas that makes stars is finite, and as it is used up, fewer new stars are born. In some tens of billions of years, the great era of star formation will be past its peak, and the universe will slowly dim. The bright, hot, massive stars go first, living fast and dying young. The sun-like stars follow over billions of years, and the small, cool red stars, the most frugal and numerous of all, will go on glowing faintly for trillions of years, after the last bright star has died, the final embers of the age of starlight. When even those are gone, the universe enters a longer and darker era, populated only by the remnants that stars leave behind, cold, dense white dwarfs slowly radiating away the last of their heat, neutron stars, spun down and quiet, and black holes, from the stellar-sized to the supermassive, drifting through a thinning cosmos. This era of remnants lasts far longer than the age of starlight did, spans of time so long that the numbers require dozens of digits to write. Across it, the dead stars slowly cool toward the temperature of the surrounding space, and the black holes grow only by the rare capture of whatever drifts too close. It is a universe of cinders, dim and slow, and yet even it does not last. For over the very longest spans, the black holes themselves fade. Through the faint leakage of Hawking radiation we met earlier, a black hole slowly gives its energy back to the cosmos, shrinking over timescales so enormous that the age of the universe so far is less than an eye blink by comparison. The largest black holes are the last great structures standing, and one by one, over spans beyond meaning, even they evaporate into a whisper of radiation and are gone. What remains is the final era, a thinly spread, ever-cooling sea of faint light and stray particles, drifting apart forever in the dark, with no concentration of energy anywhere great enough to build anything or start anything new. This is the destination the Big Freeze points toward, if dark energy holds its present course. And notice, once more, that the whole shape of this future, how fast the galaxies recede, whether the expansion eases or runs away, is set by the very component we could not name at the start of this list. There is a way to meet this that is not bleak at all. The far future is unimaginably distant, so distant that nothing in it presses on any life or any moment that will ever matter to us or to anyone we could ever know. And there is a real dignity in a universe that runs its full course gently, that does not shatter or burn, but simply, over spans past all counting, comes quietly to rest. If the ending is a long settling towards stillness, then it is less a catastrophe than the natural close of an enormous and generous story, the same way a long day earns its evening. The cosmos gave rise to galaxies, to stars, to the elements, to worlds, to us, to every question on this list. That it should one day wind down, slowly and without violence, is not a tragedy, it is completion. Notice, as the list closes, how completely the ending folds back onto the beginning. We opened with two invisible things, the missing mass that holds galaxies together and the mysterious energy that drives them apart, and we called them the 95% of the universe we have never seen. Every mystery since has, in some quiet way, brushed against them. And now, at the end of time, they are the authors of the finale. Whether the universe freezes, tears, or falls back together is decided by the behavior of dark energy, and how much structure survives along the way is shaped by dark matter's slow grip. The very things we understood least when we set out turn out to be holding the pen that writes the last page. It is a fitting shape for a list of mysteries that the first and the last should be the same unseen pair, met once at the dawn of the cosmos and once again at its dusk. Perhaps that is the right note to rest on. The universe does not owe us its answers, and it has not given them, and there is no shame in that, only the quiet dignity of not yet knowing. The unanswered is not a threat. It is simply the part of the map still waiting, and it will still be waiting tomorrow, and the tomorrow after that, patient as the stars. Let the size of it settle over you gently now, not as a weight, but as a kind of rest. There is nothing here you need to solve tonight. The mysteries will keep. Sleep well, and good night.